All right, so welcome to Practical API Security. My name is Adam Englander. I'm a software architect at Ovation. We build APIs for security, actually. So one of the reasons you'll see some security that may be way above the level you might want to do in your application is that we're a security company, so our APIs have to be even more secure. Well, that's way better. First thing I want to do is I want to set some expectations on what we're going to do here. So we have roughly 3 hours and 20 minutes to get some knowledge and practical hands-on experience with securing a REST API. I hope to show you some fairly easy concepts and applications as well as a complex one at the end. And if we don't finish that one, if you're getting the hash mismatch error, that's the complicated one at the end. There's some quick ways to clean it up that don't make sense, but I couldn't resolve that before this. So if you're getting that and you're concerned, don't worry about it. It's the last piece that we're going to do. So if it doesn't work on your machine, it's not a big deal. You'll also need Python 3. Someone came up and said I'm getting syntax errors. If you're getting syntax errors and it's complaining about the str in one of the functions, that's because Python 2.7 doesn't do typing, so it's going to be angry. If you have a Mac, I would suggest a quick brew install Python 3 to get that for you. Otherwise, there's some instructions here on how to get Python 3 installed. I'm going to do about 45 minutes of talking, and then the rest will be coding. So if you still need to get your environment set up, I don't know how quick it's going to go with everybody trying to do it at the same time in these things. But the README file for this particular project has all the information you need. Also, if you are concerned about falling behind, the likelihood you're going to fall behind is pretty small. I'm going to be doing live coding. It's not going to be slides that you have to try and catch up with. And I type really badly, so you likely type better and faster than I do, so you will probably be okay. If not, I have branches that you can get caught up with. So every section, if you're behind, you can just wipe out what you've got, change the next branch, and you can start from where everybody else is. So don't be concerned about falling behind, because that won't be a problem. Does anybody still need this URL? Awesome. So what are we protecting against? We're here talking about API security. And when you secure anything, you need to understand one thing above all else, which is who are you protecting yourself against? It's going to drive everything you do with security. And your adversaries can be different things. It depends on your application, right? If you have a dating site, right, it might be a hacktivist who thinks that dating sites are bad. If you have a gambling site, it could be a hacktivist who thinks gambling is bad. I'm from Las Vegas, right, so I get that a lot. It could be competitors, right? You may need to protect yourself against competitors getting to see your information or trying to exploit your system and show everyone else in the world that theirs is better because they were able to exploit yours. We get that a lot as a security company, people trying to do that. Organized crime might be somebody you have to protect against, right? So if you have something that has a lot of credit cards or a lot of PII in there, organized crime, you are a target for organized crime in your API. It could be nation states, right? Some of us have to protect against nation states. And it might even be internal employees, right? So we always have to know who our attackers are because we're going to have to adjust how we protect ourselves against that. Because if you want to protect against nation states, and if you want to even go so far as to be protect yourself against nation states that actually have the ability to do nonlinear math very fast, that's going to be super expensive, right? So how much work and how much money you're going to spend depending on who you're going to be protecting yourself against. So that ends up being kind of a business decision of how much money we're willing to spend to protect against what's the likelihood. And that's a whole other topic, which is doing security analysis on your system that I don't have time for. But how do we provide that protection? And one thing that security people always talk about is security in depth, right? Defense in depth is a very, very old concept. It's a military thing. If you've ever have you ever seen like a medieval castle? There are many levels that you have to get through to actually get to the things that are in the storeroom, right? You've got to get past the moat. You've got to get past the turrets. You've got to get past the drawbridge. You've got to get past the death chamber between the initial door and the portcullis in the back. Like, there's all these things you have to get through with the idea that you're going to be able to stop most of it before it gets in there, and then you'll be able to handle whatever gets in. And we do the same thing when you're securing networks and applications. So for an API, defense in depth means a few things here. It's transport layer security in the front, rate limiting and replay prevention, authentication, access control, data validation, data encryption, and logging. And logging actually doesn't fit real well at the very bottom. It's kind of on the side because every layer probably should be doing logging so that you can actually see what's going on. So for transport layer security, we're not going to go over that here because that's not easy to do without Wi-Fi and a bunch of setting up. And what that means is SSL or TLS, right? If you have an API and you need to protect it, you likely need to put it behind TLS. If you don't want people to be able to see what's coming over and you want some sort of privacy, you're definitely going to need TLS. And fortunately, that's not expensive anymore, right? 5 years ago, setting up TLS with something that browsers or applications and operating systems would have in their trusted certificate authority, that was not cheap, especially if it was going to be a fast response from that certificate authority. Nowadays, there's Let's Encrypt. Let's Encrypt provides free TLS certificates. They provide scripts to update your certificate on a regular basis. It's actually pretty good certs, and they actually just released subdomain splat certs. So wildcard certs were recently released. So if you have an API and you haven't secured it via TLS, or if you have anything that hasn't been secured via TLS, you should really consider getting it set up with Let's Encrypt. A lot of hosting providers now will just automatically, you can check the box for putting on TLS with Let's Encrypt. So it's super, super cheap and super easy, and they've managed to get a lot of things to integrate with it. So it's super easy to do. And SSL Labs is an interesting tool to allow you to review your TLS security level. Right? You may have TLS, but you have no idea how good that TLS is. SSL Labs from Qualys, it's a free tool that's available there. Qualys sells a bunch of other stuff as well, but for free they provide this, where it'll go tell you what's wrong or what's dangerous about your TLS. Are you dangerous, or are you susceptible to heartbleed? Like all of these 2 years ago, 3 years ago, there were all these attacks on OpenSSL and TLS in general. With OpenSSL and Java, a bunch of different things. And so there's Poodle, Heartbleed, oh gosh, I can't remember the other one. But they'll tell you if you're susceptible to that, and kind of you can get some information on how to update that, whether your key size is too small. If you have a website that you want Google to index, you want a 2K key. Otherwise, they will say you're not secure. And they will also be very angry with you and put you at the bottom of the list if you don't have TLS at all. But we're talking about APIs. And for the most part, most APIs, unless you have a public API that's just kind of giving out information that's available on a website, you're going to want authentication. If you're doing authentication, you're taking credentials, you want that to go over a secure channel. So you want TLS, absolutely want TLS, because that's your first layer. So rate limiting and replay prevention, that's layer 2. So once they actually get to your web server, they've gotten past TLS, whether you're terminating at UWSGI or Nginx or whatever that might be, and they come into your Python application, it's now time to see, to prevent people from being able to create a denial of service attack, right? One of the things you have to worry about is if you have something that people use, you want to make sure they can continue to use it. If you have ever tried to do something on GitHub and want, whoa, why does the GitHub work? It's usually because they're under a denial of service attack. GitHub is one of the popular things to attack with a DOS, and they do some crazy, crazy stuff attacking GitHub. You're probably not working at that scale, although you might be. If you are, or even not, right, you may want to figure out replay prevention, because one of the ways that you can prevent a DOS attack is to have horizontal scalability, but that costs a lot of money. Right? So if somebody's attacking you, your competitors can attack you to run you out of business, right? Because they will hit you hard and scale you out so that you start paying your hosting bill a ridiculous amount, and then you run out of money because you've auto-scaled against a DOS attack. And so when you're doing rate limiting and replay prevention, you're limiting the number of calls. So replay prevention means that you find some unique thing that you can require for requests. We'll go over that in depth in the examples, but you have to be able to uniquely identify this request somehow. And that may be you require someone to put in a token, put in a nonce into the headers, whatever that case may be. If you can find a way to make that request unique, you can then check to see if you've seen it before. If an attacker can just keep sending the same request over and over again, right, you can all download a tool right now that can just spin up 100 threads on your local machine and go destroy somebody's server. So you need to get a little bit beyond that. And one of the ways that you do that is through replay prevention. You find that unique value, you store it in a quick hash somewhere, whether that's local memory, depending on the size of your application, local memory. You might use memcache. You might use some other key value store like Redis, or if you get gigantic, Cassandra, something like that. So you're going to use some sort of backend. And there's really nice tools inside of kind of the Python libraries out there that give you good cache, like a kind of a backend agnostic cache. And we're going to use that in the example. But it's hard to determine uniqueness, right? Because if you have any gets, they always look the same, right? So that's why you need to add something like a nonce, right? It's some way to make that unique, some way to say, I've seen this before, I don't want to do it again. And so you store that unique value in the data store so you can verify you don't see it again. It's just that simple, right? And the easy way to do that, in all the caches that I've used, they have this thing called an add function, right? So if you're using memcache or Redis, you can say, I want you to store this, but if it's there, throw an error or return false. Memcache just returns false. And that lets you know that it's already there. So you can do an atomic operation. Atomic operations are super important, as you don't want to go check to see if it's there, and then when it's not, go put it in, because during that time, you could have gotten 1,000 other requests for the exact same thing. So the best way to do that is something atomic. If you want to use a SQL database, which for this type of stuff, I really don't suggest it because it's a lot of writes. You can do an insert statement with that as a unique index, and it will fail. It'll insert it if it's not there. Otherwise, it'll just error out, saying that there's an index constraint that you're violating. So here's an example, which is smaller than I'd hoped. And basically, checking to see if you get a token. This is taken out of the example code, so you don't have to worry about writing it down. It's all in the example code. And it just basically makes a hash of the token, which would have been that nonce. Or it can just do the entire request, however you want to do it. And then it'll add it. And if it fails, it raises if it doesn't find it, raises a 401. And if it's going to be there, if it fails on that, it should raise a 429. I have to fix this slide. So a 429 is too many requests, right? There's a standard HTTP response for that. And some of your kind of edge level caching solutions will allow you to provide another tag that tells you when that expires. So if you're using something out there, which an edge level caching system, or like a CDN, you can also do those things for your APIs, so that if you return a 429 and that's too many, they're not going to be able to make another request for 5 minutes. It'll actually add a tag, and then at the edge, they'll just keep saying, nope, too many requests, too many requests, too many requests. It never hits your app. Most of these things, it's very important to use proper codes and proper caching. So I should remember where my slide orders are, and so I don't go through this twice. So we talked about that. You can use a unique index for RDBMS. So rate limiting also requires unique identification for restrictions. So a lot of your larger APIs out there have different levels of rate limiting. So if you've ever had to use something where it's constantly getting code from GitHub, you may have been rate limited and told you needed to get an authorization token. That's one way they slow you down. So make sure that you're someone they can track and they can find out who you are and what you're doing. And it's important, though, that you be able to uniquely identify the request that you're rate limiting. So in our example, or this example, what I've done here is that I have a user. So if you want to do user rate limiting, right, you're going to concatenate the user, the thing that they're trying to do. That could be an endpoint or just an action that you're limiting, and then a time slice, right? Because you want to say, oh, if I want to do it per minute, right? If I ever see this again, if this same user does this same action in this same minute time slice, it's going to fail, right? Because I'm going to try and do the same thing I did before. So you do this, put it together, you get a hash, use the add and increment functions. So the way to see if a value is there, we've done this before, you put add. All caches provide incrementing because they're built for this type of stuff. So you're going to use the add. If it's not there, it'll put in 1. If it is there, it'll return false because it's already there, and then you just tell it to increment. Increment will return you, when you do the increment call, it returns you the current value after you incremented, and you can see if they've done too much. So another example, which isn't super large, but again, most of this is already in the code, where you're basically concatenating. This is from the code again, against a time slice. And the time slice I do just by doing an integer by minute, or by second, or 5-second time period. Again, there'll be a code example we're going to go over to kind of see how you do that. But you do a cache add, and don't worry if it fails. And then you do an increment, and then you can check against that to see if they're beyond the total that you want allowed. And we're going to do an example of that. Again, you can do the insert with unique index, and some DBMSs allow update returning. MySQL does not. Postgres does, MS SQL does, Oracle does, where you can say update this. You can say update this where the value equals old value plus 1, and then it will return the value that it created, so you can check it that way if you're doing RDBMS. Again, if RDBMS is all that you have and you have a small application, you're probably okay, but if you're trying to prevent a DOS attack, using your database for this is probably not good. If you're doing it because you have rates like, oh, you need to be a super special user to do this more, and you're going to pay me money, that might be okay, but it's not going to protect you against a denial of service. It's absolutely not going to. And when you're doing this caching, right, the data storage can be done in 3 ways. And you may want to use all 3, right? So in-memory data store. So you may want to use some shared memory if you're using things like Pyramid, and you're not using lazy loading in UWSGI, you can have a shared spot where it can put that data locally in the memory for that particular worker and share it amongst the threads if you're doing threaded UWSGI. But that's a very advanced topic, or if you're using an async framework. So if you're using Tornado, or you're using Twisted, or you've got your own Python 3 asynchronous app, you're sharing a lot of things there, and you can store it in memory there if you're doing kind of like single-threaded asynchronous I/O. That's a fantastic way to do it there, to be able to reduce the amount of work you're doing against your other server. There's a local data store, so sometimes on the same server, or if you're doing like Kubernetes, you may have another container in the same pod that's like a memcache server, local memcache server, so you're not going across the network, so it's a lot faster and a lot quicker. And each instance has its own memory for that, because memory can get crazy. And then a global data store. So you might have a Redis cluster or a memcache set of memcache servers that are on the network. And depending on what you're trying to do, what you're trying to prevent, and how important it is to you, and how much you're concerned about DOS attacks, right? The system I write is an authentication system, multi-factor authentication system. So if my system is, if you can't use my system, you can't log into your bank account. People get mad when they can't log into their bank account. They get very angry when they can't log into their bank account. So I have to protect against more than you might. So we do all 3, right? We do the memory so that it hits it locally. So if you've got a large attack, it's going to be on that server, right? It's going to be in the shared memory for that particular core because that worker's already been hit because they're hitting us with tens of thousands, right? You've got to hit us with a lot of requests to take us down. And so we're going to do that locally. So in memory, I don't have to worry about anything. I check it, it's there. I don't talk to any other servers, no network utilization, no memory utilization. It's just done. I don't want to see you, you're gone. And then we do the local cache. Then we also have a global cache because it's also across data centers. So if you're hitting us on one data center, the other data center knows about it because it gets replicated out and you get kicked off the whole thing kind of worldwide. But what you need depends on what you've got, right? If you've got an asynchronous app, in-memory data store may be perfectly fine for you. If you don't, local memcache might be fine. right? Or a shared set of Memcache servers. It's really up to you and how you want to protect it, how important denial of service and rate limiting is to your application. Any questions so far? I know I'm just kind of rocking through this. Okay. So authentication is the next layer. Once we've determined that you should be making a request, right? You're secure over TLS, you're valid, you're not abusing the system with a DOS. Now we need to make sure that you're allowed to hit the system at all. One of the biggest mistakes that everyone makes, and I've made, especially if you made a SOAP service back in the day, you probably put authentication in as part of the body because it's easy, right? You're getting in the request, you get the username and the password from the request, you go do whatever you do for authentication, and you see if this thing is allowed. The problem is that you have a lot of issues going on, especially if you're encrypting your data. You have to decrypt the data to see if they're authorized. That's an expensive thing to do. So someone can, again, hit you with a denial of service attack with you spending all the time decrypting messages that you then use to verify if they're allowed to even make the request. The other thing is that the authentication and the business logic of your application are now tightly coupled. So if you change your authentication scheme, you now have to change your application API. And your application has to be aware of how encryption works. So it can't just do what it needs to do. It has to do both pieces. It has to get the data, see if you're allowed to be there, and then actually do the business work. So the best way to do this is to use the authorization header, right? It's built into HTTP. One of the things I learned way too late as someone who writes APIs is that I should have learned the HTTP spec a lot sooner. There's a lot of really good things in that specification to help you with your job, like how to properly use cache tags and cache headers, how to properly use response status codes. And the other one is how to properly use the authorization header. And the authorization header is kind of there's some schemes that go with it, but it is just a header that's identified as this is for authorization, and it can be whatever scheme you want. Most common is HTTP basic authentication. So you're providing the username and the password, and it goes in the tag. It's base64 encoded. That's how secret it is. And it gets shipped along, right? If you're using this, you definitely need to be using TLS because your clear text passwords are getting passed across. You also should probably be talking to your consumers of your API about SSL pinning to make sure they're not vulnerable to a man-in-the-middle attack where they can just grab their credentials. But again, it's super simple, super easy to do. Nearly every framework has an integration for basic authentication that you don't have to do anything, right? It's just magic and it happens altogether. But again, it's passing credentials across in plain text, which is not super secure. There's digest authentication. Don't use it. It makes things a little more complex, and it gives you a false sense of security because you're not setting a clear text password, but your options are an MD5 hash or a SHA hash. And if you're not in the know, MD5 and SHA-1 are so insecure. There used to be a time when there was this thing called a rainbow table, is that you had, here's the hash and here's the value. People went through all this trouble of finding every combination to make a rainbow table to do a quick lookup. Today, it is quicker just to brute force the hash than it is to look up in a large index. So MD5, SHA, if you're using those for passwords, you should stop now. And digest authentication uses that, and it's not super helpful. And again, if I just know your hashed password, I can use it too, right? So it adds a nonce, which helps some. But again, it's super easy to figure out their credentials just by brute forcing the SHA hash. There's tools out there to do it in minutes. So just don't do it. There's bearer authentication. So bearer authentication you may be familiar with if you've ever used OAuth or OpenID Connect, which is based on OAuth. And that puts a bearer token. That's a very small kind of a representation of a bearer token. They are usually gigantic, and we're going to use those in our examples. But if you're going to be using a bearer token, you need to make sure that you're using a JSON web token properly, because things are going to parse these expecting them to be actual bearer tokens. One of the first mistakes we made with our API is we decided to go use our own custom scheme, but we put bearer in there because we were using a JSON web token, just not the way you would normally use it. And because we did that, certain things started intercepting it and going, oh, I'm going to use OAuth, and it just blows up because it's not actually OAuth. So we had to actually just disable some stuff in the framework, which was fine, but it was like, oh, bearer token, I know what that is. I'm going to authenticate, and it fails. But if you are using OAuth, again, perfectly acceptable, OAuth 2 with a JWT, you can do that. And it's doable, although there are the only negatives to it that I see is that you now have to have an authentication service, right, that's going to provide that token. That's problematic. And so if you have applications, like most Python applications, client applications aren't stateful. So if you're going to make that call, you don't have that token stored for later use. And if you do, you may not be storing it securely because that's a whole other mess to have to store that. So you've got to have, make 2 calls for every call that you make. So I've got to go get an auth token, and then I've got to make the call. And that slows things down. And if people are constantly slamming your auth server, maybe not so great. And then you have to make an auth server, right, where that's a separate application or that's part of your existing API. They have to have a way to pass credentials and get a token. So you're still getting credentials one way, right? But you're giving them back a token that they can use. So if you have a need for OAuth or a need to provide that, it's perfectly fine. Although if you don't have an idea of what you want to do yet, it may not work out as well as you hope, depending on your application again. What most people do is roll your own, right? A lot of APIs do this. A lot of APIs roll their own. Even APIs that claim to use OAuth. If you've ever used the Twitter API, you've seen that it's OAuth plus, right? They add a bunch of extra junk in there that's poorly documented, that you have to have things in a particular order or nothing works. But most of us, even myself included, I was always told, never roll your own crypto, right? I am not a cryptographer. I am not an expert at this, so I shouldn't do it. I'm becoming more of an expert at it, but again, there are certain levels I'm willing to go to, but I'm not going to write my own encryption scheme. Because that's just not what I do, right? I write APIs. I write business logic. I turn customer requests into actual endpoints. And that's what I'm really good at. So I leave it to the experts to do that. So there is a middle ground, though. And what I use is a single-use JSON Web Token. So it's using all of the loveliness of a JSON Web Token that you see in OAuth or OpenID Connect. But the beauty of the JWT is that there's no auth service required, a single-use JWT, right? So the client creates a JSON Web Token and ships it along, and you don't have to hit an auth service. Another advantage to it is that there are existing JWT libraries in every language to do JSON Web Tokens, right? The beauty of the fact that JSON Web Tokens are used for OAuth 2 and OpenID Connect is that every language has at least 1 and sometimes 10 libraries to do JSON Web Tokens, and you can figure out which one you like best. And initially in doing the Python stuff, our API, we had 3 because one did one piece well, one did another piece well, but that got out of hand because they were all using different crypto libraries, of course. But you can use these libraries to create and validate. So if you're having to write an SDK, because once you start using something like this, customers rarely can do this on their own, so you might have to write an SDK. But the amount of code you have to write for the SDK is very small because there's a library that you're going to use to make the JWT. And it can be extended beyond auth to provide data validation and man-in-the-middle protection. So by definition, JSON Web Tokens, which are, all a JSON Web Token is, it is a specification for a JSON object. And it's extensible. There are specified keys, which are part of that token, but you can also put whatever keys you want of your own in there. And so what we've done is we've added additional things in there, and we'll talk about it a little bit for the data validation side, that we put into that JSON Web Token that gets signed for every request so that we're validating all of our request data to add that in. Again, we probably have to be more secure than most people. May be interesting, something you may want to use, may not, because it's not super simple. Access control. So now that I've validated you are who you are, and that you're allowed to hit the system, I need to make sure that you're allowed to do what you want to do, right? And that's where access control is. You're a valid user, but are you allowed to perform this action? And as in all security, by default, you should have no access, right? Everybody should be intrinsically denied, and then you put in your exclusions inside of that. And they should be based on user credentials, right? So it should be, there's a bunch of different ways to do access control. There's a bunch of different systems for doing access control, but if you want a secure system, you want to make sure that if somebody screws up, everyone's going to be denied by default, as opposed to everybody's going to be allowed by default. So something to absolutely think about whenever you implement access control. And then you determine based on information in the request and the authenticated user as to whether or not they have the ability to perform that action. And my suggestion for almost all of this is that your access control logic should live outside of your controllers, right? Your application logic shouldn't have to care if somebody has access. It should just have business logic. So if how you do that changes, you don't have to change all your controllers, and you don't have to have this ridiculous amount of mix and multiple inheritance to add all these pieces into your controllers that's shared amongst everything else. I did it both ways. It's so much easier when it's not part of the controllers, I promise you. Data validation. So standard security is that you're going to validate your data. There's some really good libraries in Python to do that. We don't really go over that so much in the examples because, again, there's just libraries that just do that. If you want to validate form data or if you want to validate JSON data, the libraries are there, just use them. But you may also want to validate the request itself, which is, again, data, right? Protecting against a man-in-the-middle attack. So message validation, again, super easy. Just make sure that you're not getting data that could be harmful, and it's data that you expect, right? There's some, Python's usually not so bad about this. There's some horrific examples of things that you could do in JavaScript with Node. One reason is because validation, if you do data validation with regular expressions, which is fairly common, Node.js is and if you have a single-threaded application written in Tornado or Twisted, you should be worrying about this too. If you validate via regex, people can actually take your entire system down by providing a large enough string that the regular expression stops the whole process as it goes through trying to do these matches. If you have a complex regular expression, it can take minutes to process a large enough string. Right, so if you don't have a very well-defined string or you don't check length first, right? First thing you do when you validate data for a regular expression is you validate length, and then you match it against your regular expression because even just a standard UWSGI application, you've got a thread that's locked. And if they send you 1,000 of these requests, every one of these threads is locked for 2 minutes. So they're actually performing a denial of service. So bad things can happen when people send you bad messages. And if you have a single-threaded application, it only takes one request to bring down an entire server. All right? That's one of the problems about single-threaded and blocking. But request validation is another piece, right? If I modify request data, some pretty bad things can happen. So let's take this request here. I hope everybody can see it. So it's a GET request, a standard GET request, right? But if I were able to intercept that and change it to a delete, bad things happen, right? And that's not all that hard to do, right? If you're able to man in the middle, take the request, modify it, ship it on, I don't have to change the credentials. I don't have to change anything else, right? I have an authorized user who hadn't made this request before, perfectly valid request, but I'm turning gets into deletes. All of a sudden, there's nothing in your database, right? Bad times. Another thing is that let's say I have a valid user in the system. I'm a valid user, but I want to see another user's information, and I change the URL in the middle. I got the wrong data, right? I'm seeing somebody else's data, or they're getting bad data. Another thing in the body, right? I can change somebody's email to my email, right? I just wait for patch requests, and every time I see that email come in, I just change it to my own email address, and I'm getting all the emails for everything they were supposed to get. Response validation can be super important too. Perfectly valid, 200 okay. But if I change it to a 400, it's basically creating a denial of service because you think it's down. all you get is errors, right? Your customers think it's just down. The other thing that is even more dangerous most of the time is 301 or 302. Because I can change the top piece, add another header at the bottom, and tell you, and a lot of clients, if you're using an HTTP client, make sure it does not follow redirects by default, and you probably want to make sure you're telling it not to follow redirects, period. Unless your application specifically does redirects, most REST APIs do not, so don't follow them. But they can tell a client to go somewhere else and get the data, and inject bad things all over the place and do terrible things. Cache control is another one, right? So I can, again, make people think your system is broken by changing a cache control no cache, which means hit me every time, to never hit me again. So I can give you, whatever answer you get is the answer you'll get from now until the end of time. And if you have things like Java clients hitting you that are running on application servers or .NET, that will stay in there in that client for months. And they will not make another request to you for a long time, and they will not get updated data. It's just terrible, terrible things. Because they have built-in caching to reduce the amount of things, right? Caching is awesome. It says, this thing's not going to change for 5 minutes, don't ask me again. Great, except when it's wrong. Cache invalidation is a difficult thing. The other thing is you can also change data, right? If someone wants to see if I'm an active user and I change false to true, right, bad things are happening. So validation of request data and response data is a huge thing. Request data for the server, response data for the client. And if you want to be validating response data, that usually means you're having to write an SDK. So you can decide, again, how important that is for you. But if you want to build in a secure API, you want to make that as restrictive as possible, right? You want to make sure that what you're getting is what you're getting. And you're at an API security talk, so I probably don't have to argue with you that just TLS is fine. It's already there, nobody can mess with it, and you'll be good enough, right? Because it's not necessarily the case. It's just not. Data encryption. So if you have data, and if you have EU data in another 16 days, it'd be super important for you if you have EU data. You need to be able to encrypt that data at rest. And if you're like me, and you've been doing this for years, and you've been doing it poorly for most of those years like I have, there are a few things that I can give you that will make it a whole lot easier. One is use a structured format. Most people who encrypt data have a single key that is not known to the database or of whatever store you're using, and they encrypt that data, and then one day they have to change the key. And they have to create, field new. And they have to go re-encrypt all the data into field new, and then they have to go change all the code to use field new, and then they have to go switch it back over. There's better ways to go about that, to provide for key rotation. The other thing that you probably are using if you're doing that is you're using a static initialization vector for your encryption. Initialization vectors are what create uniqueness amongst all the data, so that if you have two values that are the same, encrypted, they are different, which is super important for encryption. It's a whole study in how to create randomness or uniqueness inside of encrypted data. And the way that you can do that is if you can use a structured format. So Jose, which is the binary brother of Jose, I'm not kidding, it's the same group. It's the CBOR object signing encryption. So Jose is JavaScript object signing notation. Jose is CBOR object signing encryption. And if you don't know what CBOR is, which I didn't before I researched this, was the concise binary object representation. If you're old like me, you probably remember certain data protocols, which the names are escaping right now, especially in banking, where you had this whole protocol that said, first 2 digits tell you what character it is, next 3 digits tell you how long it is, and then the data, right? That's CBOR. It's a kind of standard generic way of doing that, which is hilarious because we left that to go to XML, which everybody hated. So they went to JSON, which was too verbose, so they went back to CBOR. So if you've been doing APIs long enough, it's all come full circle, which is hilarious. But Cose is something there's not a whole lot of libraries. There are going to be more. If you've heard of FIDO or web authentication, web authentication uses Cose to shrink down the size of the data so that you can. Right now, it's not helping you much on HTTP 1.1 or HTTP 1.0, but on HTTP 2, all messages are binary. So when you send binary data, it's a lot smaller. When you do it across HTTP 1.1, you're going to have to base64 encode it, so it can make it across. But for the future, it's prepared for the future, and that's what Cose is. But if you don't have a library or you're concerned about availability of libraries, you can roll your own, which is what I do. And basically, you have data that's going to have a key ID, a nonce, and then the encrypted data. So you're storing all the information necessary to decrypt it. The only thing that's missing here that you could add if you wanted to, and it's one of the things that CBOR will have, is the algorithm. So if you want to change your algorithm over time, you can do that as well. The way that I do it is I use null bytes. So I make it completely binary. I take a key ID, turn that into binary, null byte, nonce, null byte, and then the encrypted data. Stick that in the data store as binary, so it's not using up more space than it needs to. And then when I pull it out, I can see, oh, I need this key. Here's the nonce, decrypt it. And the nonce is actually, depending on what type of cryptography you're doing, it's either initialization vector or just an actual nonce. You're probably using AES, so it's going to be the initialization vector. Any questions about that? This is one of the more confusing ones. No? All right. Encrypting data in transit. So that's when people send or receive data from you. And most of the time, that's difficult. Relying on SSL and TLS for sensitive data is problematic, right? I live in Las Vegas. Las Vegas is the home of DEF CON, and they prove every year why it's a really good idea not to send information over TLS, right? As they attack and hack everything. You do not go to the Strip during that week with a phone that is turned on because you will be hacked, right? Anything that you think is safe is not safe. And if you go to a couple security conferences, it'll just blow your mind on just how unsafe things are. Because there are a lot of things, especially if your clients, the people who are consuming your API, aren't enforcing TLS, right? A lot of people are like, oh, I have to use a proxy, so I'm going to turn off certificate verification. Or someone could just respond back with another certificate from a certificate authority that's been problematic. There's been a few that have been removed in the last year that have been removed from Mac OS, SE Linux, and Windows, but on older installations, they're still there, right? If you haven't updated your trusted certificate authorities, someone could pass along a cert for your endpoint that's perfectly valid with a CA that's already been hacked. So that's something you got to worry about. And again, at the very beginning, we're talking about defense in depth. So for the most part, when you try to do this, if you've had to encrypt data before, you're like, well, what would someone I trust do, right? You say, well, what would Amazon do? What would Google do? What would Facebook do? And if you look at them, most of them have some sort of encryption thing, but it's really weird, and it's their own thing, and it's not something you could easily port to your system without having to write your own SDK. And again, most of us in here aren't cryptographers, so we probably shouldn't be doing that. Google can write their own because they have cryptographers, right? Amazon can do that because they have cryptographers. You probably don't. So my suggestion for you is JSON Web Encryption. So JSON Web Encryption comes to you from the handy-dandy people at Jose who make JSON Web Tokens and JSON Web Signatures. And JSON Web Encryption is an open standard that provides multiple encryption methodologies. So it allows you to use elliptic curve, it allows you to use RSA, it allows you to use AES. You shouldn't, but it will still allow you to do triple DES. There's a lot of things that allow you to do none. It's actually an option. It'll allow you to specify keys, to do key rotation. It also creates a MAC at the end for verification. It's really, really interesting and good stuff that's built into it. And there are libraries for most languages. So we implemented this for our API. And the only thing we had a problem with was iOS. There are Objective-C libraries, but we use public key cryptography, and there was no implementation for RSA. We had to become cryptographers and write our own implementation for RSA. Fortunately, they have tests. In the JWE specification, there are tests that when you do this, you should get that. So it was actually really easy to do it, well, relatively easy to do it and make it compatible. But most of us aren't writing iOS apps or communicating with iOS apps. But if you are, you want to use JSON web encryption, and you want to use public key cryptography, we're looking to open source the solution at some point, but it's not now. But most people don't use public key cryptography. They use some sort of shared key, and it'll be just fine. And we're almost done with talking. Logging. So this may not seem right, but log everything. Right? One of the problems that we have as software developers is we want to minimize. Right? That's a lot of noise. Right? I don't see all that. It clutters up my logs. Log everything. And there's the reason for that is that when something goes wrong, you have to know what happened. When you're under attack, you have to be able to know. And there's a lot of information that can be gleaned from your logs, like who came in, what did they access. You may want to be able to have something that's going to parse 404s and figure out, oh, this IP address keeps hitting 404s. That's an attack. I'm going to shut them off. So there's a lot of things you can do. But it becomes a lot easier if you log it in a structured format. Just kind of spitting out text isn't super helpful, especially if you want to parse those logs. So using a structured format, Python logging makes it super simple, right? You can just specify the formats in there, and there's also a couple of examples for doing it in JSON, just in the Python docs. Log all the pertinent actions, right? Things that you care about that people might be doing. Include all data regarding state, but anonymize sensitive data, right? So you have to know what people are doing. This person tried to do this to that person. So you can identify who's under attack, because it might be somebody who's attacking an individual. And you can find that out, and then that individual might be able to help you find out who's trying to attack them. And you want to include origin data to identify bad actors, right? So you want to make sure you have an IP address. You want to make sure that you have, if you're taking in and they're sending across the HTTP client the request, right? You want to do that. If you have information about origin, where the request originated from, you want to try and capture that because that might give you some insight into what's going on. And you can use tools like Elk or Graylog to aggregate logs. That's an entire talk on talking about that, and probably not best at a Python conference. You probably, wherever you're from, somewhere in a 50 or 100 mile radius, there's probably a B-Sides, security B-Sides conference. They'll tell you how to do all this kind of nonsense, on how to do all this. But your application, in order to use all these systems, in order to be able to use all these systems to aggregate logs and to alert on problem things, you have to have all the data, and it has to be in a structured format. So if there's things that you want to do or something you might want to look at, consider doing that. Because that will help determine anomalous conditions and be able to alert on those conditions. All right? When you're trying to prevent attacks, most attacks are insidious, but there are a lot of conditions like someone who's, this type of person should never be trying to do that, right? If they're using our API correctly and they're using the SDKs, this would never happen. So that means that's probably an attacker, and you probably want to stop them. Or alert your networking people that there's something going on, or automatically just send something to the router that shuts them off for 5 minutes, whatever you need to do. Or in your own internal system, just turn them off, right? You can rate limit them to 0. Or put them in a dead list, a blacklist where they can't hit. There's a bunch of things that you can do, but you have to be able to see a lot of data across your entire application, and that really only happens with logs. And with that, we'll take a break because I have talked a lot and you have listened a lot, and you probably need a drink and probably need to use the restroom. So let's make it a hard 10 back at 220. Okay, so don't let the tiny text fool you. It's going to get bigger, I promise. So if you had any difficulty in setting up, I got a lot of people who sent me emails saying that they were getting, at the very end, they were getting an error from the client with an exception with a hash mismatch or unexpected hash. Don't worry about it if you got that. The hash part is the last thing that we do, and it's some absolute weirdness that I can't figure out why it's happening. Sometimes it does, sometimes it doesn't. If you deactivate and reactivate your virtual environment from the server and the client, that fixes it most of the time, which makes no sense. So we'll try and figure that out, but again, not a huge deal. Verifying the request hash and response hash is the last thing we'll get to. It's the last piece. So hopefully, based on that URL that was up there earlier, you have, see, I'm trying to run CMD. Hopefully you have installed or cloned down this repository. Hopefully you've also set up a virtual environment. Come on. Some people also had difficulty because they were trying to run this in Python 2.7. The first place I experienced the hash mismatch was in Python 2.7. The client would do a 3.6 server fine, but the server would then give an invalid hash mismatch. So I was actually converting the code to 2.7 and couldn't get it to work, so I just backed it off, and we'll just have to rock with 3, because if you're not using 3, you probably will be very soon, because 2 is like end of life in a few years, so you should really consider moving. There's even talks on doing that at the conference. So once you have that and you have the repo cloned, master branch is where all the code is. We're going to do some coding here, and again, like I said in the beginning, there's branches that have pieces removed. So we'll start with start here, but then if you get behind after start here, or at any point in the project, that's fine. We can just check out the branch that's at the next spot, and we'll take off from there. So nobody has to worry about falling behind because they didn't get a piece done. If it's a little overload or it might be a little much, I put this in as an advanced topic because some of the stuff is fairly advanced, although the typing isn't very advanced. And it's not terribly difficult to do, although grasping the concept might be tough sometimes. So what you want to do is you want to check out the start here branch. Let me move this up. Hold on. That's the very bottom of the screen, but nobody can see, right? So you want to do a get checkout, start here. Can everybody read that, or do you make it bigger still? In the back? Can't read it, right? Is that getting better? Okay. I know I probably wouldn't be able to read it back there, but I probably would have sat up front. So yeah, you just want to check out the start here branch with using Git. And that'll get you to the base code. So when you actually go look at the code, get into presentation mode, which will make this easier. So you can see it. Everybody see that okay? Okay. Okay. So you should have a fairly empty server file. And what we have here is we have just a fairly plain Jane vanilla Flask app that has a bunch of things that don't exist yet. We do have a couple things that are not in a normal Flask app. Is we have a default error handler. So what it's going to do is it's going to catch exceptions. HTTP exception is something that we have here special. I like to have named exceptions because it's easier to catch them other places. And basically, we've added some validation inside of our route. On a lot of APIs, I put the validation outside of the route because the route doesn't care about validation. It just cares that it has data. But that probably would have made it a little overly complex to add that as well. And the validation is so simple, I just put it in the route. I specifically use Flask just because you can see most things in just one file. We'll actually use 3 whole files. One just holds the exception, the HTTP exception. One's going to have our event handlers, and then the rest is just this page, this file here. All this stuff is super doable in Pyramid. My APIs are in Pyramid, although we're moving them off of Pyramid because a lot of the cool stuff in Pyramid we don't need anymore. It gets in the way a little bit more. But Pyramid actually has middleware, where Flask does not. I absolutely suggest doing this stuff with middleware, and you'll see why in a minute. Because we're removing the concern from the controller, it's super easy just to put things before and after the controller to modify the data in the way that you want, to validate it before the request happens, to sign it after it goes out, to decrypt it before it gets processed, to encrypt the response as it goes out. So middleware is awesome for that. Flask doesn't have middleware. Flask has event handlers, but that'll work just as fine. If you're using Django, middleware, not a problem. So if you have a Django API, it'll actually make more sense probably, be a little easier that we're doing here. And so we have a route. That route has 2 methods, get and post, and it's the /route. And the handler checks to see if the method's post. That means it's getting data. There are ways to separate that differently, but it was just easy enough to do it in one small chunk here. I wouldn't probably normally do it that way. I'd make get and post different methods. But and then it's going to validate the data. All right, so it just makes sure that the length is between 0 and 26, and it doesn't care about anything else. If it's not right, it raises an HTTP exception with what's wrong and a 400, which means invalid request. On a type error or key error, which means it's not a string or it doesn't have that key in the data, same thing. It needs to be a JSON object with the attribute 400. You'll actually get that error if it's not valid JSON in the body. So if it gets something else, if you get binary data in the body, it'll blow up correctly. If it's not post, then it's assuming that the name is world. And literally all it says is hello world, right? Returns a JSON object, hello world, right? So if we go here and we start our server, which I'm going to have to go back to the README to find it. That's not the README. That's not it, but the README is here. Try again. That's okay. I have backup. The Wi-Fi is not working. So I always forget how to start Flask servers. It's super, super easy, but I always forget how. Okay. Right, so we're going to start our server, export Flask app equals server.py. We can put it in dev mode, but it doesn't really matter. Flask 1, it does matter, because Flask 1 is development mode, it'll reload, but we're not running Flask 1 because I couldn't get that to work either. And then we just want to do a Flask run. And if all things are good, it will start up, and I got a server at 125.0.0.0. Right? So because it's just a standard REST server, I can just go to a standard thing here and just do a quick curl. And get back hello world. Right? We're up and running. We've got our base API, one of the simplest APIs you could possibly do. You can also do a post. -d. Actually, it has to be single quotes. Name Adam. And that should work. Which it didn't. Oh, I need to do X post, sorry. That's why. Must be a JSON object. So I did something wrong. But that's fine. So we've got a post going through and otherwise. Having to do all these curls, super annoying. So I made a client, which is the other thing you had to try. So if I just do client Pi, it's going to make the request, come back with a response. So there's nothing in the request. And then if I put in that, it actually does that, so I don't have to remember curl. Most days I remember it. Some days I forget how to actually put the stuff in there. So this client will do everything you need to do, and after you get out of the class, there's some, we'll see a little bit, but there are different flags to turn on encryption, off encryption, get certain errors, see how things don't valid. You specify an invalid key ID, specify an invalid key, see what happens when people send wrong data, and kind of play around with it. Plus you can see how that stuff all kind of works a little better inside of code, I hope. It also has verbose mode, which will actually show you the response that came back. So here's the request that I sent, the actual HTTP request. So if you want to say, hey, what does this actually look like on HTTP level? If you're an HTTP geek like me, you might care because it makes more sense to me looking at it like this than any other way. So that's the request that got sent and the response, the actual response. So we sent content application JSON, we got back application JSON, the content length, all that kind of nonsense. So we're using a nonce authorization of none because we're not doing any authorization yet. So hopefully you're able to get this far. Because this is basically what the installation and configuration settings from the instructions would have gotten you here. If you had any of the errors that we were talking about when you switched to this branch, all those errors are magically gone because you're not using that right now. Something quickly I wanted to talk about, but not too long, is the requirements. So most of the things you probably feel like there's Flask, there's Blinker, which was needed, but I needed a particular version of Blinker. And then there's requests, which is a standard Python request library built on URLlib. If you've never used it, it's super popular. And the basis of most every other HTTP client that's out there. And then there's PyJWK EST, which does some of the magic. So there's amazing things and terrible things about PyJWK EST that I wanted to get out of the way. Documentation, it would be kind to say it's sparse. Many times I've had to just go into the code. So I understand JSON web encryption and JSON web keys and JSON web signatures and JSON web tokens, which is, by the way, what KEST is. JSON web key, encryption, signature, and token. It also uses algorithm, which is JWA. But it's an effective library that actually does everything that you need to do with all of the different pieces. And there's a pro and con to this as well, is for doing the actual crypto, it uses PyCryptoDomeX as opposed to PyCryptoDome. So PyCryptoDomeX is a userland encryption implementation. So it's pure Python. So if you have a small application and you have no control over what's installed and you can't install extensions that build binaries, you will love this. If you have a large application that uses, that you do have that kind of control, it does not provide, or it does not allow, because it runs completely in Python, it does not allow for chip-based AES acceleration. So if you have a large application that's doing a lot of encryption, PyCryptoDomeX will be a problem. So it's my job over the next 6 months to start making pull requests for PyJWK EST to add documents and documentation, because it is, like I said, I know this stuff already and I have trouble finding it sometimes. So anyone who's new doing it is going to have a bad time. And the other thing is that I also needed to work on PyCryptoDome because I need AES acceleration because I have to handle a lot of requests per minute, and I do a lot of AES encryption. So being able to use the chip to accelerate that, actually every server and most clients and all non-Android phones have on-chip AES acceleration. So just a little thing there. But again, there's not a lot of requirements here, and request is only used for the client, and PyJWK EST does all of our encryption, all of it. All right, so we're on server. So the first thing that we want to do is we want to add in replay prevention, right? It's not a ton of code, again. And what we're going to do, like we talked about before, is the first thing we're going to have to do is we're going to have to create, because I always do this with my code, is I'm going to create a signals file, which, whoops, I already have a signals file, right? So first thing we need to do is signals. So signals is what is actually why you need Blinker, because we're using signals. And Blinker is required for doing event handling, right? So if you want to build, it basically puts in an event bus. If you're a Java person, you know about event buses. If not, then you might know about event sourcing. But it's the way that it's creating an event system. And what Flask calls events are signals. So it's going to signal you that the request is starting. It's going to signal you that the response is complete, things like that. So the first thing we're going to do is we have to, for making sure that we're doing replay prevention, we have to have uniqueness, right? So that's actually the first thing we have to do. So what we're going to do, so I don't want this handler, don't want that handler. Okay, so for replay prevention, we're going to need cache, right? So the thing we're going to do is we're going to store this in cache. So we're going to create a new class, and we're going to call it the rate limiting signal handler. This is the first time I've typed something in a month without a typo. All right, actually I don't need that because it's Python 3. Oh, actually I do, because, and the rate limiting signal handler, right, doesn't need that. So we're going to create an init, right? So you've got an init, and we're actually going to pass some things in there. First thing we're going to pass into it is we're going to pass into it a cache. So we get cache, right? And we're using the and I hope someone could tell me this weekend how to pronounce this. I pronounce it Workzug because it looks pretty German and it looks pretty close. The Workzug. Sorry, I'll slide it up. I think. Hold on. Let me shrink this. I can't. Question?
Is that a colon at the end of that?
Yes, that's a colon. I think it's angry because I don't have two. Yeah, it's angry at me because of Pepe. So we're going to initialize a base cache. Another thing we're going to do is, because it's usually a good idea, because normally this would be configured through some sort of configuration, is we're going to get rid of this. We're going to put in a rate count, which is an integer. Right, and we'll store that to a local variable. There's my first typo. Right, so cache equals cache and rate count. Equals rate count. Okay, super easy stuff. So now we're going to have to inject into our signal handler a base cache and a rate count. The reason I do this is testing. We're not going to write a unit test today, but if you want things that are testable, you have to do injection. So that's just the way it goes. So the next thing that we have to do is we actually have to write our handler. And so it's actually going to handle request started. So I'll just call it the request started handler. See, I can't type. Especially on this keyboard. I got this new Mac, and I can't stand the keyboard. There's nothing more frustrating to me. Seriously, like in a long time. That's replayed. Okay. And that's so. And this thing gets sender, right? It gets sender, and then there's extra stuff. We don't actually use sender, but this is how it's defined. All right. So, and right there is enough for it to actually be a function. Yes, you're too many lines. I know. Thank you, Pep8. All right. So the request start handler. It's an instance method which takes the sender and a bunch of other junk that we don't use any of it, so it doesn't really matter. Because unfortunately, the only way to access the request in Flask is through a global singleton object. Yay! So we'll just do that. But the first thing, so in order for us to actually, that's rate limit, I won't replay. We need to get a token from the request, right? So so I need to get a token from the request, and I'll pass it the request, which is a handy dandy function which isn't written yet. So and we'll do that so it doesn't get angry about the fact that there. So we need a token. So the first thing we have to do is get a token from the request. It's actually fairly simple in this iteration, although it's going to get more complicated as we go along. But the first thing we have to do is we have to get an authentication header. Oh, I probably want to actually tell it it's a request, don't I? Yeah. This just makes my autocomplete easier. It's not required just to type it. All right, so I do request.headers, get, all right. So if you saw in the client, we were sending along unencrypted body. We're sending around an authorization header of nonce. All right, so I created my own little ridiculous scheme called nonce, and it's just going to send a nonce. All right, that's all it's going to do. And so we will be able to use that to determine if a request is unique. But we're going to send none, right? So what we're going to do is we're going to send the same value every time so that we can actually get it rate limited. Question?
Should it be authentication or authorization?
Authorization, you're right. Thank you. Yep, authorization header. It's probably right here in front of me in the text. Oh, actually the code is wrong. And we'll default it to blank, which is probably fine because it was erroring anyway. And Unicode, right? Yeah. So we're going to default it to a Unicode blank string if we can't find it. Then the other thing we have to do is after this horrific regex, which I apologize. This one actually doesn't need it. So for this one, we're actually fine with just a straight authorization header. We'll need the other stuff later, but we'll just return the authorization header for now. Right, because this is a unique value, right? It's going to have this. In theory, it should be providing a nonce, and we'll get back a different value every time. So we can just use the header as our unique identifier, because we're just going to hash it anyway. As we get along in here, we'll have something a little more complex for uniqueness, and we'll use that. And it'll be required for us to do some regular expression nonsense. Okay. So next thing, we are going to make sure we have a token, right? So if we don't have a token, we want an error. So if token is none, we want to throw an authentication error. All right, so that should be, if it's none, throw new HTTP exception. sorry. Wrong language. Raise. HTTP exception. Come on, type. Authorization was required. And that will be auth required as a 401. Okay. So now we've made sure that you absolutely have to provide authorization. Right? It's just a key right now, but if you don't have this, I'm just not going to let you in, which means that most attacks come from people who know nothing about your API. They're just trying to see what's there. And if they don't provide that header, they're going to be rejected. Now, security through obfuscation is not, it's not something you want to aspire to, but you can just stop people from just randomly hitting your site and being able to do terrible things with a scan. Like there are some scans that are so aggressive that it will take down your site for the whole time it's doing the scan because it's just spidering and spidering and spidering. So you can just tell it to go away if you do that. So if we've done that, we're great. So now the next thing we need to do is we need to actually go see if we've seen this before. All right, so the next thing we have to do, if not, self cache add. So we're going to do that add we were talking about. Right, and so add takes a key, a value, and a timeout. And the cache, you can set the default timeout, or you can set the timeout value yourself. I'm just going to go with the default timeout, which I think is 5 minutes. Right, so I need the key, and the key is the token. If you wanted to, you could hash it. It doesn't really matter. Hashing it makes sure that someone can't just go look at the data, because there's been a very recent thing for a nice vulnerability people have, which is called cache poisoning, where you can just figure out what the key is and throw that into their unprotected cache servers. So if you're using memcache, right, there is no protection against that. There's no authentication necessary. So if someone gets on your network, they can just start throwing in the cache values. So not being able to figure out what that is so easy might help out, but we're just going to put in the straight up token. And the value is true, because we don't need a counter or any of that kind of nonsense. And if we don't get it, then we're going to get a invalid request, right? Request is not unique. That's a 400, right? Let's scroll down. It's going to go into PEP 8 rage, but yeah. Yeah. It is somewhere in here, but yeah, I have no idea where. But I'm okay with PEP 8 rage. Like, I'm not going to submit this for code review. We're good, right? So all we've done here is we've just created functionality to get a request, and then find some uniqueness inside the request, however that works. We're going to make sure we get our token because we require it. And then we're going to try and add that token to a cache to make sure we've never seen it before. Right? That unique value, we're going to put it to a cache. If it's there, cache add will return false. Right? So we know that we've seen this exact request before. We should fail. And that's what it will do. We're not using it yet, so this is fine. And again, we have separation of concern. We have signals which are separate from the rest of our code, and they're just going to work like magic, right? We don't have to modify any of our code, so you can take your existing handlers and make it work, right? So we go back to our server, right? And then way up here, we're going to add in this junk, which I have to remember how to type it in on the server. All right. So we're going to instantiate that signal. Replay prevention signal handler. And I use very long names. It's not really good for this particular demonstration, but it helps me know what things are in my code. What do we end up calling that? Replay prevention. Oh, Python. Yeah. Sorry. All right, and it's going to need a cache, which we're actually going to share the cache. So we'll have. Sorry, should probably do this in order, right? So first thing we need is cache. We need simple cache. So simple cache is just going to use the file system. You would not use this if you were doing this in production, but we're doing this here on our boxes on a single server, so using the file system is fine. So that's what simple cache is going to do. All right, so it needs cache. Yep, not there. So our replay, thank you for that. And let me import. Did I? Oh, that's right. Sorry. I was looking at the wrong code. This is next. We called it rate limiting? We shouldn't have called it rate limiting. I apologize. This should actually be replay prevention, is it not? Sorry. This should be replay prevention. Rate limiting is next. Replay prevention signal handler. My apologies. Because we're actually doing replay prevention, right? Okay, and it's also going to need, a cache. It's going to need a rate limit, or a time. No? What does it need? Actually, that is all that it needs. Did we give it time? We gave it a rate count, and we don't need the rate count. I apologize. I was one step ahead of myself. That's why I called it the rate limiting. So you can get rid of rate count. I apologize. All right, because we didn't use any of it in any of this. So we're trying to do replay prevention. All we care about is that we've ever seen it. We don't care how long, when that might be, whatever. Yeah.
Where's the request variable coming from?
Request variable is imported here from Flask import request. It's a global singleton. Yay.
So then what is sender?
Sender is, this is the definition you get when you look up signals. Sender, I haven't used it. I don't remember what's in it. And it contains some information about the signal being sent, but I don't remember. I think it's just part of Blink. Somebody else here may know better than I do. I don't. Okay. So again, it's a singleton. There's a bunch of things in here that are just global singletons, which is annoying, but it is what it is. And I couldn't find a better way to get around it. There's no way to get it from the event. So you do what you can. All right, so now that we have our properly named replay prevention signal handler, which just gets the base cache, because we're now typing the right code. Come on, go away. So we have our replay prevention signal handler. Now that we have it, we actually have to register the method. So we have to register the signal. And so there's this thing called request started, which is, again, it's just a function. And we need to, on connect, we need to connect this receiver to it. All right, and so we're going to pass it the replay prevention signal handler. And that should just be it. Let me double check so I don't screw you guys up again. Oh, request started handler. Sorry. It wants the function. Request started handler. And we have to pass it the app. So the app is the Flask app. And so we're registering, this is the way it's going to be registered. So request started connect requires the app so it can actually tell the app that it's going to be being used. And we're passing the method that's going to be used to be called when the signal happens. And that should be it, which it is. Okay. Say that again? Handler. which is why it was angry. Thank you. Typing is not my favorite thing. If I did not have an IDE, I would not be a programmer. Because my typing is terrible. It's really slow, and I make so many typos, and it's gotten so much worse with this new Mac. At work, I'm fine because I have their old regular keyboard, and I'm good. But anyway, so now that we have that, and it should be working. So now, sure, yeah. Yeah. Yeah, so what you're doing is you're telling the request started, which is something that's already imported, should be. You're telling it to connect our handler, the request started handler, to the app. And so it's going to link all that stuff together. Right? And so now, if we do our curl, it should not work. We should get a 401. Which we don't. Oh, I didn't restart the server. Sorry. Got to restart the server to get the new code. And it didn't blow up. Yay. Still for 401.
Is that because we defaulted to the
Oh, you're saying we defaulted to a string instead of none?
Yeah.
That could be it. Which would have been. Yeah. Thank you. Yeah, that should be none. So it should error. And that was my mistake all the way through. So we get authorizations required. If we use the client, it should go through because we're going to provide it. But if I do it again, request is not unique, right? Because we sent the same thing across. So again, one of the super important parts of using middleware is that none of my business logic knows anything about this. As far as it's concerned, it does not exist. But we were able to add security in on the application side. And we're going to just keep adding stuff there. So they're having a break here with snacks. And the snacks will be there in 2 minutes. And they said you should get out there before everybody takes all the snacks. So I guess we'll take a snack break back at 3:10. Everybody got good. If you had that problem where you were getting the positional argument required, oh, sorry, let me turn on the mic. So if you had the error where you got the positional argument not found trying to set the cache, you have to instantiate the cache object. The positional argument was value because instead of sending self, you weren't instantiating the object, so self was replaced by key, value was replaced by key, and all that stuff. So what that meant in actual language and not been talking too long stupidity was, not this one, in your server py, you have to make sure when you do this that you actually instantiate simple cache. So if you were getting the error which said the missing positional argument 2, positional argument 1, if you actually instantiate the object, if you had it like this, you would get the error. Which makes a lot of sense when you understand about Python functions because you didn't pass self, so it moved everything left 1. And so now it makes sense. Okay. So I hope everybody is running from this point. I think there were some people that were kind of stuck, but we're all kind of moving now. We're all good? Yes. Yes. I try to do that when I'm typing, but then I have to go find pages, and it's not easy to move around this thing. Okay. So we've got a replay signal handler. Next thing is the thing that we did half the work of. You've probably seen most of it already. Is that we actually need a rate limiting signal handler, right? All right. So that's the next thing we're going to need. And it's going to be similar. and it's going to use some of the same functionality. Let me get up my notes so I don't do it completely wrong. Although, as you've seen, that doesn't always stop me. Okay, so we need an init. In the init, we're going to pass in again. What we actually did the first time is we need cache. Come on, Python. We need a base cache. We're going to need the rate count, which will be an integer. And we'll do rate seconds, which is also an integer. Okay. Yeah, so in this one, we're trying to instantiate this handler. It needs cache, so that it can be incrementing values inside of a cache. It needs a count, which is how many are allowed. Now, this is a very simplified one, which means that we are just rate limiting globally. The same values globally. So we're going to create our little token based on our request data, but we're not going to be doing things based on different pieces. The one that I actually have implemented in my API, we have different rate limits for different types of things. Right? You can authorize all you want, but you can only, actually we limit the amount you can authorize. There's certain things that have different levels. You can authorize at different levels too. We have multiple rates. So you can do so many per second and another so many per 5 seconds. Kind of rate limit that way. So again, you could add other pieces on top. You could have multiple signal handler or rate limiting handlers, or you could just have one very complex one. We're writing a super, super, super simple one. Oh, it already did that for me. Darn it. Okay, we're good. So we have our cache. Right, so, oh, sorry, this is, I've been talking, I should have been just doing this. So we're going to save our cache. We're going to save our rate. What are we calling it here? Rate count. Then we're going to save our rate seconds. So now that we can do stuff. Next thing we're going to do is we're going to make our request started handler. Def. And I'm calling these request started handlers. You can call them whatever you want. But I'm specifically calling them request started handlers because that's what it's going to get registered for. And it makes it a little easier because some of them have request finish handlers as well. This is not one of those, though. So we get self, we get sender again, and we get extra. In theory, you could just put ** extra and not put sender, but this is how they do all of the examples, and I want to get as close to the example documentation inside of Flask that I could. Okay, so first thing you have to do is you need to get a cache key. So you don't necessarily have to make it as a function. I prefer doing it this way. It's just me. I like to make it obvious how that's actually happening. So important things for cache keys are the time chunks. So time chunk says when you're doing rate limiting, you're saying, I'm going to limit you to X number of this type of request over this time period. And in this particular one, we're passing in the number of seconds, right, the rate seconds. So we're going to say that I'm going to limit you to rate count requests over rate seconds. So we have to get a time chunk to make for the hash, so that when that period of time expires, it's a new hash, and so you're incrementing something else, if that makes sense. So the first thing we want to do is we want to do some fun math. So we want to do the int of datetime UTC now, although it doesn't necessarily matter that it's UTC, but I always do UTC and get the timestamp. On Python 2, this would just be time. Yep. Oh yeah, equals, yeah. Yay. Okay. So we've got timestamp. Stop that. Timestamp. And then we want to divide it because timestamp is a double precision. It has milliseconds, and we don't care. So we want to get the integer of that, and we want to integer divide. Everybody knows the double slash, right? That means divide this and just make it integer. Love Python. And we're going to divide that by the rate seconds. All right, so now we'll have a value, time chunk, where it's going to be the current time divided by seconds, right? And it's going to be an integer. So that's a unique value for that time period. Make sense? So if we're doing it every 5 seconds, you'll have the same value for 5 seconds, and then once that 5 seconds is over, the next 5 seconds will have the same value. Because you're dividing by 5 and getting an integer, so it's always going to be the same. And that's like the simplest way to get a time chunk. The next thing you want to do is you want to build a key, right? And I prefer to use delimiters to separate the pieces. So we'll just do this handy mess. Yes. So yeah, string formatting, and so we're going to pass it the request path, request method, and the time chunk. So the way that we are identifying, uniquely identifying the request is from the path and the method. In my application, it's way more complicated than that because you could make the same request, but it's based on, you can only make so many auths per user per minute. You can make as many auths as you want, but it's based on per auth per user that requires some investigation of the request. So ours is actually after we decrypt the request, and we figure out what the user is on a user request. But again, that's all, none of that's in the controller. All of that is in middleware, and that's a special function that we get, oh, it's this path, so there's going to be a user there, so I'm going to go get that and figure out the time chunk and see if they've done it. But now we have our key. Once we have our key, we're going to do our add. All right? Return key, sorry. You have to return the key. And now we're back into our function again. And so we're going to get our cache key. That should have actually been get cache key to be less confusing. Sorry. I'm going to rename it. Call it whatever you want. Doesn't matter. So we're going to get the cache key. And then we are going to increment the cache key. So but we need to make sure if it's higher than that. So we'll take our cache, and we will increment the key by 1. Oh, sorry. Yes, that's right. I'm sorry. Increment cache key. You don't have to put 1. You can just say increment because it'll default to 1. It'll be easier for you guys to read, so it won't be too long. And we want to say if it's greater than the rate count. If it is, then we will raise an HTTP exception. Too many requests. And that's a 429. Now let me get this up higher so people can see it. Okay. So now we have an event handler that's has a function to generate a cache key. We'll get that cache key, and then we'll increment that key inside of our cache. We're incrementing it by 1. And when you do an increment, the return value is the current value of that cache key. So in an atomic nature, it will increment it and return you the value, and you can determine if that one request is too many. So if it is more than the rate count, then we're going to raise an exception. Otherwise, we do absolutely nothing. We need to implement it inside of our server. That's not what I want to do. Go into our server, and we'll do this again. Request started, connect. Oh, sorry, first we have to actually implement the, this one is rate limit. Rate limiting signal handler. I assume I spelled it right, yes. So the rate limiting signal handler, and it needs cache, count, and seconds. So we'll pass it the same cache. We'll say 1 every 5 seconds. So you normally wouldn't have it this low, but I want you to be able to actually see it fail, which should be super nice. And then we're going to connect it. So the rate limiting request handler, request started handler, and pass it the app. Let me close that so you can see. Okay. So much long stuff. Long names make it very difficult here. Yeah, so we instantiate a rate limiting signal handler by passing it the cache, the same cache used by the replay handler. We pass it the number of requests, which is 1 every 5 seconds. So if you send 2 requests in 5 seconds, you should get too many requests. Again, you wouldn't normally do this low, but for you to be able to see it in the example and be able to move along, it's a lot easier this way. And then we register it, the rate limiting signal handler, request started handler, and we pass it the app just like we did before. That's it. So we should be able to restart our Flash server. We run this once. It says hello. We run it twice. The request is not unique. Why is the request not unique? The other handler is broken then. So let me look at the client. The client might not actually be sending it. So let's go take a look at the client real quick. I may have turned that off on the client. So on the client, no JWT, issuer, audience, JTI, claims, get request data, method, body, headers. So it's not adding in the nonce, which is why that is failing. There it is, authorization nonce, format JTI. Okay, so if you delete line 92 in your client, it will work. So line 92 was taking this value and setting it to none. And so it was setting none as the header, which is a bug in my stuff, and I apologize. So it's client.py, line 92. It looks like this currently, and it should be gone. This whole line should just be gone. And then it will work. Yeah. 200 requests. Right, so now we're doing that, and if you do that, it goes fine. You do that. I must have passed over. Too many requests. If I change it to a get, it's fine again. Right, so it's based on, from what we had here, that's not the code. We had here in the code, in the signal, it's creating uniqueness for this cache key by the, wow, that's impressive. The cache key by the request path, the request method, and then the time chunk. Right? Seems super simple, and it really is. It's taken me years to get it to be that simple. But that is a very, very basic rate limiter written in like 20 lines of code. So yes, question?
I'm not able to reproduce, I'm not, so it's still working for every every request, it's not that
Every request, is it giving you, the request is not unique? Yeah, so line,
No, it's returning hello world every time.
every time it should.
okay, did you instantiate the handler? So in the server.py, so it has to do the connect here. You have to do request started connect, rate limiting signal handler. Oh, restart the server. Is anybody else having that same problem? Okay. So we can get back, but if the code's done correctly, it should work. I promise. Don't feel bad about it, don't worry, yeah.
So why is the replay prevention broken at this point?
The replay prevention wasn't broken, the client was just setting the same value every time. Replay prevention was working, the client was broken. So you're setting a new value every time. So JTI, sorry, I'll explain that better, I apologize. So the JTI is a UUID, which is a universally unique identifier. And a UUID is a random value. So it will, by machine name, it basically puts a bunch of information based on the host and then adds randomness so that it's unique to that host. And because it has information about the host and a unique value, there cannot be a duplicate value of that anywhere else. So it's a universally unique identifier. And it's a random one, via 1. So we're now generating a new value every time. So replay is fine because it's not seeing this request more than once. Yes?
Does it maintain order when you add handlers?
It does. The order that you put them in matters. And let me go look at the actual code to see what the order really matters. I think it's actually inverse order of the way that you put them in. Because the next ones will start mattering. When you decrypt data and sign it and all that kind of stuff. You want to validate it before you decrypt it. But we will probably do crypto first to make sure we get as much in as we can. Okay, so we all ready to go on to encryption? Yes?
People have problems starting the server over and over again. Just in server.py, you can just pass an app.run, debug is equal to true flag. It will automatically restart and check this.
Okay. Yeah, so if you export Flask debug equals true, right?
Yeah, so if you switch to server.py file there,
Server.py file.
all the way to the bottom, then you have to start. So app.run, you can pass in debug as required here, is equal to true. That should
Let's start restarting for you.
make any changes here afterwards.
And if you have syntax errors, will it completely crash? You have to restart again too? Yeah, that's why I didn't do that. I had the same problem with containers too. It's like, oh yeah, because this thing it's fine if you're using Vim, you're probably okay. But in this editor, when I leave the window, it saves. And even if I'm not done typing, so you're going to have code that doesn't work, it won't compile, and it'll just blow up. So, yeah. So if you want to have it automatically restart, you can put the debug equals true in the app run. But we're not actually running this file, so it may not work because we're doing the Flask app run, so it actually won't work either. Yeah. So if you just run server pi and do it that way, it'll work. Okay, so encryption. So we're going to the, as far as the controllers are concerned, this is transparent encryption. They're just going to know that they just got the same request they got before. But the client will have to either encrypt and decrypt the data that's going across, right? So we're going to create middleware inside a signal that's going to decrypt a request that is encrypted, and it will encrypt all the responses. That too is not a lot of lines of code. The important thing is that the keys match. So the keys are hard-coded in this one. You wouldn't normally do that, but we're just going to do that. So encryption is the super simple one. Sorry about the tapping. I'll move that over there. Okay, so we're back to signals. And we're going to make another signal. And this time it's going to be the encryption signal handler. Oh, class, I'm sorry. Typing is not my thing. All right. And this is going to need some different stuff. So one thing we're going to need a list of keys. Which are a list of string, I believe. Oh, list of key, my bad. So you're going to need a list of keys. If you look up here, you can see what keys actually are. It's jwkest.jwk.key. So this is a JSON web key. It should need more than that. Nope, just needs the keys. And because the way that the encryption stuff handles, it's not like there's some of the problems with JWK EST is it's not super testable because you have to instantiate a new object every time based on the way the keys work. But it does the trick. And we use it in production and it works really well. So the first thing we want to do is actually want to store those. So we store the keys. Next thing we want to do is we want a request started handler.
Is this just a name you're naming? You can name it anything?
Anything you want. Yeah, it's just an object. It's a class.
Okay. The function request started. You can
Yeah, name it whatever you want. Okay. Yeah, because you're just going to pass that function to the actual request started. Yeah. It just, I do it this way because it's what it is. So it's easier for me to figure that stuff out. If some other naming convention makes sense to your organization or to you, use that. I just do it this way. So again, we're going to get sender and args, or extra actually. Extra. Okay. So the first thing we need is we need a JSON web encryption object. JWE. Yay. The next thing we need to do is we need to decrypt the data. Decrypt. Token. So the token is actually going to be the request body. And do we want to wait? Yes. So let me do one thing. We're going to want to do some insertion about that real quick. So one of the things that we can do for this to make it so that it is kind of blind, if not all of your requests are going to come in encrypted, you can check to see the MIME type and make sure it's what you want to do. So we'll add that in just so it makes a little more sense with the examples. So if request content type equals application JSON. Sorry, application Jose, which is the registered type. That means it's going to be encrypted. Double equals, yeah, I do. That's why it's angry. Yeah, so basically what we're saying is that if the request is application JSON, that means it's encrypted. I know what it is, and I can decrypt it. I can assume that it's got all the information necessary to decrypt, which it actually does. JSON web encryption includes the algorithm that was used to encrypt it. It includes an identifier for the key that was used to encrypt it. It also generates random keys every time. If you're using elliptical curve or RSA, something that encrypts based on the size of the key, and you want to use that, but you can only use very small packages, it will actually randomly generate a key and IV for symmetric encryption and do that, and then just encrypt the keys and ship those over. So it's this really fantastic magical library associated with this fantastic specification at the IETF. And they really have thought about just about everything, right? Every edge case you could possibly come up with has already been resolved, and solved with Jose. So we're also going to need to pass this. Is that still working? It's got a lot quieter since I don't have the mic pointing at me. Okay. So to get the encrypted stuff, we're going to have to pass the data and the keys. So basically it's saying everything is needed to decrypt it. The information that it needs to be able to decrypt it is inside the packet. The thing that it needs is it needs the packet and the keys to decrypt it with. That's all you've got to give it. So we're going to do that. And the next thing we're going to do, and this is a wicked little hack that you have to do because this is not middleware. I'm hoping to find a better way to do this. I haven't found one yet, but you can modify the request. because it's a super global singleton. So we're going to do that. Normally, you would make a new request. If you're having middleware, you would take the old request, you'd make a new request with this new decrypted data and tell it that it's application JSON instead of application Jose, and then everything else would just deal with it like it was that way. But since you're not actually given the request and you don't ever pass it on, you have to modify the request. And since it's Python, you can do that, right? Because you can do anything in Python. It's magical. So there are some things you shouldn't mess with normally. One is cached data. So what we're going to do is we're going to set the decrypted value. Cache data equals decrypted value. And then we also want to set request JSON. Right? Oh, sorry, request cache JSON. As JSON loads decrypted data. Now you probably should have some more error handling in there if you want to do better things about you gave me invalid JSON, stuff like that. It'll get caught by the error handler, and this is just an example. If this was a real live application, you would never just let these things bubble up through. You would want to see if you got a type error, if you got some JSON errors, then you would want to handle those appropriately with 400s instead of just returning a 500 error. But I wanted to make this as simple as possible without adding 700 lines of error catching in there, which I normally do.
You do need to update the content type?
Yes, we will update the content type. Actually, we don't need to. Normally you would do that, but you don't need to because it's just going to go get JSON, and it's going to use the cached JSON. Which most apps, they're going to do one of two things. They're going to get the data, or they're going to get the JSON. So we've set it so that it will use either. You absolutely could set the content type. I believe it's available, so we can do that too. Although in the rest of them, it doesn't have that. So if your application cares what type it is, you can do that. The other thing that you can do that we're not doing with this is that the type can be set in the packet. So when you have the encrypted packet, it has a CTY header, which is the content type header. So if your application accepted multiple content types, it could take XML, it could take JSON, it could take YAML. You could actually specify the content type in the encrypted data. So when you decrypted it, you knew that, oh, this was application JSON before, so I will now treat it like application JSON. We're not doing that in here because it's always just JSON, right? So now we have a way to decrypt everything. And that's our decrypt everything. So if I send it an encrypted response, it will now decrypt it. The other thing we need to do is we need a request finished handler. This gets different stuff, I believe. Yes. So we get self. We get sender, of course. We get response. And we get extra. So the request finish handler is going to get the sender, which it always gets, and the response. So we're going to be able to read and write to the response. What we're not going to be able to do is send a different response. So again, we're going to have to modify the current response because that's just what happens when you have events. You get passed by reference the piece. Yes?
Do you need an underscore content type on line 63? Or is it different? Request dot underscore content type?
No, it's just content type.
How come they're different?
So this one is not supposed to be messed with, right? In Python, putting underscore means this is shared amongst anything that inherits it, but you shouldn't touch it externally, but you can, right? So it should be taken as a warning. And by the way, messing with this can have bad consequences because the application, that the module that's using it, the class that's using it, may not have ways to be able to react to the fact that you changed it. But this is the only way to do this in Flask that I know of, that I can find, without actually doing UWSGI middleware, which I do not want to do. So it's not great, but it is what it is. Like, even if you use __, it's much more difficult to find it, but it still has a very specific way of accessing it, and you can absolutely do it. But like I said, you shouldn't do this, and I had to go look at all the code to see what would happen when I changed this, because there's a lot of things that happen when you change this that I had to go make sure what was going on. So this is what would normally get set when it actually parses the data. So that's why I changed it there, because there's no other way to do it inside of Flask. Again, if you're using Pyramid, it has real middleware. If you're using Django, it has real middleware. Flask does not. So you're having to do some kind of crazy stuff. Any other questions real quick? Okay. All right, so what we need to do now is we need to start encrypting things. So we have a request finish handler. First thing we want to make sure is that we're not getting an error. So we want to make sure that the response status code is between 200 and 300. So if it's 300 or greater, that's a redirect. There shouldn't be any data. If it's a 400, it's an error, and we probably don't want to encrypt our error response. If it's 500, it's a server error, that kind of stuff. So we only want to encrypt responses where the status code is a 200 code. 100 shouldn't have data either. Yes. Yes. Thank you. No. Yeah, you're right. You know what? Yeah, because all the stuff we actually do only does 200, so it worked. Normally, you'd have unit tests around this stuff. And that would have found that. I'm not doing a testing course this year. Okay, so if it's actually that type of stuff, if it's a response with data, and you might want to say you want to not do 204s or check to see if it has data, because a 204 shouldn't have any content either. So this is just a quick example. So the first thing you want to do is you want to get the response data. Come on, response, get data. And you want to get data as text. That's important. Otherwise, you'll cast it to a string, and you'll have the REPL amount of representative amount of, which is different from the actual text value of the response. So you would have a byte array that would then be turned into a string, so it would have like B, single quote. You don't want that. So you want to get the response as text. And then you want to create a JWE with that data. Right, so we're going to pass it the data. You're going to pass it the algorithm. So there are a lot of different things you can do. What we're going to do is we're going to do AE. So algorithm is the encryption algorithm it's going to use to wrap the keys. So even though you have your own keys, it's going to encrypt the data using random keys. So that it always works the same way. It's also going to create that random key because it's going to create some random values or some hashes at the end, and that makes that unique. So it's going to create a MAC at the end to verify the data, and that way your MACs aren't the same for the same data, just because your keys are different. So it helps with to prevent cryptanalysis being able to figure out what your data is. And if you want to be super secure like I do, you're not using symmetric keys, you're using asymmetric keys like RSA or elliptical curve or something like that. So the algorithm is what you're going to actually encrypt the keys with. And so our algorithm is going to be AES 256 key wrap. The algorithms that are available are in the Jose spec, which is an IETF spec under JSON web algorithm. So the little shorthand stuff is all in there. Okay. And then we want to provide how we're going to encrypt. So what we want to do is we want to encrypt using AES 256. AES 256 CBC. If you don't understand AES 256 CBC, so this is advanced encryption standard. 256-bit key using the cycle blockchain mode. This is probably the one you want to use. If your system supports Glockhoy's counter mode, you could use that. No, there's no guarantee that it will always be supported correctly, so you probably want to use CBC. It's considered one of the more secure ones. GCM is better, but it's not necessarily always supported well because it requires that it has a unique counter for every single time you encrypt, and if you can't verify that or don't know what that means, then you don't want to use it. So CBC is probably good enough. And then we also, for the MAC at the end, we're going to use an HMAC, SHA 512. So we're going to encrypt the data using the key wrap algorithm of AES 256 key wrap, and then we're going to encrypt it using AES 256 cycle block chain using an HMAC with a SHA 512. And hopefully, it may not make sense to you. It doesn't necessarily matter. If you use this every time, you're safe. And if you were using RSA for public-private key pairs that you exchange, you would just change the algorithm to, I think it's just RSA. So you would just, you're still going to have the AES encryption of the data. You're just going to encrypt the keys using an RSA algorithm. Okay, yeah. All right. So now, and we did set the content type. I'm sorry. So the other piece we're going to set in there, it's optional. I like setting it. Right, we're going to set the content type to application JSON. And this just means that anybody that's receiving this encrypted packet knows what's in the data. It's a super awesome feature that's really forward thinking that any encryption, any like roll my own encryption thing I did, never thought about this. So yeah, so it knows you're passing into the data that's in there is, the content type is application JSON. Okay, so now we need to actually encrypt it. And encrypted is going to be JWE encrypt. Question?
Could you read out the keywords there that are difficult to read?
Sorry, ALG. Talk about these keywords here.
The last ones.
Okay, so ALG equals A256 key W, ENC, ENC is encryption, A256 CBC HS512, CTY, which is content type, equals application JSON. And the CTY is optional. So next thing we're going to do is we're going to encrypt the data. So we're going to pass it the keys. And we only actually have one key in here. So we're just going to use the key ID from key 1. Because you have to tell it you're going to pass the keys and which key to use. You may have, if you have more than one key, you're going to have to come up with a better way than just passing it the first one. But since we're only ever going to pass in one encryption key, it's perfectly fine. Oh, sorry, .key ID. And so what this is doing is that when it goes to encrypt it, it's going to use a key, and that key has an ID. The ID can be whatever you want it to be. When I do RSA stuff, we actually do a hash. We do the fingerprint of the RSA key so that it's easier to figure out if you've got the right one or not. And it's not magic, but if you're using RSA keys, it could be, you know, you could name it key number 1, key number 2, whatever, if you have multiple keys. But you have to pass the identifier so that when it gets it back, it knows which key it used to encrypt it, so it can get that key with the key ID and go decrypt it. Which is the same thing here, because if you see in the decrypt, we just passed it the keys. It had to go find which key it used to encrypt it by the ID. So each key is going to have an ID in there, and you'll see that when we build it here in a minute. Okay, so that's all you have to do to get the decryption. Right, so then we'll send the response content type. Content type equals application JSON, or sorry, application Jose. So that the client knows this is now encrypted. And we need to set the response content, or data, sorry, response data. equals encrypted. So quick recap. If our response is a 200, and we should actually probably say, what's that? So if the response status code is between 200 and 300, we get the data from the response, we create a JSON web encryption object, give it the data, the algorithms, and the application type, or the content type. We encrypt it using the keys and a specific key ID, because it only encrypts with one key. And then we give it the response, the content type of application, Jose, which is the same thing we set up here for the incoming request, if the content type was Jose. And then we set the response data to the encrypted value. And so now, we have to actually go set that up on our server, which is fairly simple to do. Basically the same thing we did, except now we have a request and a response. So let me go back to my server. Okay, so now we need an encryption signal handler. And it's going to need keys. We'll put keys in there in a minute. We'll do it here. So I've got it doing in line, so I'll put on a new line so it's easier to read. Okay. So what we're going to do is we're going to have, it's just an array of sim key, or list, sorry, wrong. So it's a sim key. Its use is encryption. Its key ID, KID, sorry, its key ID is key 1, and its key is, I'm going to have to copy this. That's over in the client. So the key value, you probably want to copy this from the client, which should be somewhere near the top. The default value of the key here. So in the client on line 21, you can copy it from the GitHub. It's a very long key. I probably should have made it shorter. Easier to type. Question?
How are these keys shared? How does the client...
So in a symmetric key system, right, you find some way that you pass the key to both people. Not super secure, but you can do it all day long, right? If you've got Amazon Web Services, your API key, that's your shared key. There's an asymmetric key option with this. There isn't with AWS. Right. So if you want to do an asymmetric key option, right, you would use a different algorithm. So you would have a public-private key pair, and then you would use the private key to decrypt, the public key to encrypt. You'd use the same key ID because they both come from the same thing. They both have the same fingerprint. And then again, you would have the public key encrypted, the other one decrypted, and you're still using AES to encrypt the data, so that the size isn't restricted by the size of your key, but it generates a random key and IV, and then it encrypts those and sends them along.
Do you consider that overkill?
I use it.
Symmetric?
I use asymmetric as often as I possibly can because, and this is one thing I talk about a lot, is that when you share a key, right? If me as a customer, I have to believe that I have to have a lot of trust that the company that I'm working with doesn't give someone else my keys so they can't steal my data. And as a provider, I have to trust that someone's not going to just put their key in GitHub and then people are going to have untethered access to my system. So I'm a big proponent of asymmetric keys, specifically using RSA because it's so widely available and supported. And so we do that, and it's actually really nice that one of the problems that you have with RSA encryption is that it doesn't do rounds. It's not a block encryption methodology, so you can only encrypt to the size of the key. When you do this mix mode here, it removes all of those limitations because it's going to encrypt it in AES, and then it's going to encrypt the keys using RSA. Any other questions? Yeah?
What Python
So for this particular thing we're doing right now, PyJWK-EST. It does everything. It uses PyCryptoDomeX. Which I would prefer if it used PyCryptoDome, and I'm going to work on that. See if the contributor, the guy who wrote it, is open to that. Because PyCryptoDome allows for AES acceleration. So again, for the key, copy it, because having to type that, maybe you could, I can't. So we're just going to provide the key. So the signal handler, the encryption signal handler required keys. We just have one. And the beauty of this is you can have as many as you like. So key rotation is a real thing. And you can rotate your keys as often as you like, as long as everybody knows about it. So if you're in the process of rotating, right, your system can have multiple keys active at one time, and you're just using one or the other to encrypt. So it's actually really nice. Because if you've ever had to work with a system that only has one possible key, that the second you go generate that new one, everything is broken, which is terrible. Don't do that with your APIs. Please don't do that with your APIs. And so we're going to just provide the keys. And then we're going to actually register handlers in the beginning and the end. So we need a connected handler. So the encryption handler, we're going to put that up top. So request started, connect. Then we're going to use the encryption signal handler, request started handler, and pass it the app just like we always did before. And then we're also going to add a request finished handler. And we're going to pass it the encryption signal handler, request finished, and the app. All right, so very large, very hard to see. Very large, very hard to see. So we added the request started connect here with the with the encryption signal handler and the request started and the app, just like we did before. And this one, we're also doing the request finished connect. So when the request is done and it's written the response, we're going to get triggered, and we're going to take the response data, and if it's a data response of 200 response, we're then going to encrypt the data and ship it back. So I think I've only failed this once. So with any luck, whoop, deleting expired sessions. Damn you. Okay, export, Flask app, server.py. Oh, sorry. I have to be my virtual environment. That's what happens when you kill tabs. Bad things happen. Yeah, we're good. All right. So now we're running. So now this shouldn't actually be able to decrypt it because we haven't enabled that in the client yet. So when I send it, it hates me. I have a bug. Invalid CBC HMAC key length. Interesting. Did I do something wrong? So it's angry about my key.
It thinks somehow it's using the key 1 as the key and not as the index.
Okay. I'm not sure. Let's find out. No, that's right. Use encryption, key ID is key 1, SIM key, list of keys, ends in an 81. Ends in 81. Interesting. So let's see what we did wrong here. It's got to be something wrong in the signal handler. So, and this was trying to, is it on encryption or decryption? Okay, so it's trying to encrypt the response. So request finished handler, JWE, algorithm. Get back to the page. Server signals. Da-da-da. Oh.
So for the encrypt method, you have to pass a keyword argument as a second.
I didn't do that? Let me look here. So what do we have here? We have alg, enc, A256, CBC, HS 512. Self keys. Oh, you're right. Sorry. Key ID equals. Yeah, so in line 69 of signals, we missed, I missed, not we. I take full responsibility. Yeah, you have to tell it the key ID, because that's actually a different, what is the second one? Yeah, content encryption key, which we did not actually pass. That's why I was complaining about the content encryption key, because it was way too short. Because you can specify a different content encryption key as opposed to an encryption key. We didn't provide one, so it's going to randomly generate one. I wouldn't. Like I said, I honestly, my content encryption keys, if you don't trust random generation, then provide one. But if you don't trust random generation, then you've got bigger problems. Stop, restart. All right. And the likelihood that you're going to make a better one is pretty slim, I think. Cool. So this one actually decrypted the body, but if you see here, this is what you got back.
What is the command you are running to send an encrypted body?
I didn't send an encrypted body, I just sent a body, a decrypted body. There's the nonce, and I didn't send anything, I did a GET request, and the response came back encrypted. If you want to send an encrypted request, so if I actually put my name in here, all right, still not sending encrypted, you can go into the client and enable that. Right now it is hard-coded to not encrypt. So if you just comment out that line, content no encryption equals true, it will use the settings. I didn't want it to encrypt until we got to encryption, so I hard-coded to true. So that would be line 31 of client.py. If you comment that out, it will now send encrypted data when you send requests. Now remember, this one worked whether you sent it encrypted or not, it didn't care, right? It just said, oh, if you sent it encrypted, I'll decrypt it. And I guess we should make sure it actually works, right? Error read-only property. Ah.
Should we be using set data in the response instead of response data equals? Does that matter?
Let me go see what this is erroring as, because it's very angry right now. I'm not quite sure why. It's not telling me why either. So let me see what was actually here, and it might actually be, maybe we are supposed to use set data. Because this was working before. So this actually, I think, is an issue with the response, because it worked fine with, it's the issue with the request, because it worked fine with the response. So let me make sure I'm doing what I thought I was doing. So we changed content type, and I don't think you can. Maybe that's why I didn't change it. Because this is something that isn't in the regular code. So we're not going to set content type. Because I think that's the read-only property. Oh, yes, it is. It's a property function, so you can't change it.
You have an option in the client just to accept the national encryption.
So right now, the way that you have it set currently, it is hard. It has that, but then it's hard coded to false because it wouldn't know how to deal with the encrypted data. So on line, yeah, there's a line 31 is where it's hard coded. So if you just comment that out or remove it, now the flag for no encrypted will work. And if you remove the setting of the content type in the request, then it will stop blowing up.
In both places?
No, just in the request. So we're taking the request, we're taking out the decrypting it and putting it back. That doesn't work. Because it's just a property, because it reads it out of the headers. It's a special thing when it loads it. It's a function, because it may not be there and it goes and reads it and all that kind of nonsense. And so now, my server should not be broken. And when I run it, it's perfectly happy. So one thing I want to get through really quick, we're not going to be able to get to the JWT stuff. 3 hours is apparently too bold. But all the code is there, and it's a very, very advanced feature for authentication, where you take a standard JWT and you expire it. It will immediately expire. It's only good for that moment. And what we do at Ovation, and the code is there as well, is we add request data in. So we put the request method in there. We put the method, the path, and then we hash the body. And so that is signed. So part of your authentication is you're signing this token using your credentials. And so instead of hashing it and signing it at the same time or in separate things, we just put it together since the JWT is extensible. So if that is something that really intrigues you, I will be here all week and could talk about it forever. Most of you, it will be way too much, I promise you. Most of the stuff that we're doing now, like the encryption stuff, can be used with any type of authentication. And for most people, basic authentication or OAuth is fine. It depends on who you have to protect against, right? But one of the things I wanted to get into, because we still got a few minutes, is I want to talk about what is known as Jose compact encoding. So anytime you look at something with Jose, whether it's a JSON web token, and you'll be able to start doing this actually in your, if you're using anything that uses OAuth, it'll have that token in there, and you can actually start parsing it and reading it. So the way that it's built is it's base 62 JSON encoded, although you can base 64 decode it. There are extra characters that get turned into different things. But you shouldn't run into any problems. So, and it's separated by periods. So encrypted data has 5 segments, right? This is your JSON web header. These are your keys that are key wrapped. This is your IV. This is your data, and this is your MAC for authentication. It's your auth header. And what you can do is you can take these things. Come on, you know you want to go. And you can just base 64 decode them. So if you're having problems and you can't figure out what's wrong, see it's actually missing stuff, so you have to put in. It doesn't include padding. It removes all the padding. So there's your proper thing. So here is our algorithm, A256QW. Content type is application JSON. Our encryption is A256 CBC HS512, our key ID. So if you want to make sure this is working right, you can just copy these things out. You can take these out of your request or your response. You can base 64 decode them and see what's going on. You can try manually decrypting the data, right, to make sure it's correct if you know the keys. If you're running into difficulties. So it's actually it's all JSON, basically all of it. And you can just take a look at the pieces and parts just by base 64 decoding it. When you initially look at it, it's this magical stuff with a bunch of junk, but now you know it's just JSON separated by dots. Some of it's encrypted, so it'll be binary when you base 64 decode it, but some of it's actually just JSON. So we've only got like about 7 minutes. Any questions about any of this? Do you have a hand? Does it go until 4:40? So that's at 4:20. Oh, it does? Okay. Then we'll go for another 30 minutes. Awesome. Everybody cool?
Yes.
All right. Let me see what we can do. Let me see if I'm brave. How about this? I'm going to switch my code over and we'll talk about it because I don't think we have enough time to type it because it's a lot of typing. How about that? Are we good with that? Because if I have to type this, it'll take me an hour, right? If I have to like look at my phone and type and look at my phone and type, it's going to take forever because that part is complicated enough I can't remember it. So let's actually just, and you can do the same thing unless you really want to keep all your code. I'm going to reset all of that. I'm going to go to checkout master. So now, all right. So inside of signals, oh, awesome. I made an extra file called name Atom. All right. So here's a bunch of stuff. So the token signal handler. So this is the JSON web token signal handler. It has a lot of stuff in here. So keys, it gets a different section of keys, different set of keys, because unfortunately, even though they don't always have to be this way, certain algorithms have different keys for signing than they do for encryption. AES is not that way, but you still have to specify a different set of keys. So you're going to pass in the keys. You're going to pass in leeway. Leeway is important for time drift. So anytime you use JSON Web Token or use anything that requires minute values of time, you have to be allowed, number one, for time drift, and number two, for transport time. So if you say, I'm going to expire on this second, and you send it at the end of that second and receive it at the beginning of the next second, it's going to be expired. So leeway is the number of seconds that you're going to allow for differential. With an immediately expiring token, you have to have a way for the users to be able to synchronize their time with your system. So our API provides an endpoint that gives you our time. Our SDKs go pull that up every, I think it's once an hour, if you have a Java client or .NET or a resident Python process that's constantly running, the SDK will go get it, and if it hasn't, if it's been over an hour since it got it last time, it'll go get it again. Because you probably won't drift that much. But there's the possibility that when you first start, you could be off by a minute, right? Most of us think, oh, you're off by a minute, whatever. With an automatic expiring token, you're done, right? Your leeway doesn't work. You would have to create a leeway way too large to be reasonable. So that's something you have to think about if you want to implement this. Cache. So we're actually going to be ensuring that certain things are unique inside the cache. And then claims. So claims inside a JSON Web Token are exactly what they sound like. I am claiming that I am this. And then it's up to you, when you receive them, to validate those claims. So you're going to get an issuer. Is this issuer a valid issuer? Is it who I'm expecting this to come from? So when you're sending a single-use JSON Web Token from a user, myself, the user, I'm the issuer. I'm issuing this token. Audience is who's receiving the token. So in an OAuth world, issuer would be you, the user. Audience would be whoever you're giving the token to. Or, sorry, issuer would be who you got the token from. So if, let's say you're using Google to log in. Google would give you the token. They would be the issuer. You would be the subject. And then wherever you are authorizing that token to go to, when you say, let this person log in as me, right? So let's say you're using Google to log into AWS, whatever. Google's the issuer, you're the subject, AWS is the audience. So that token is only good for AWS and you. So it can't be used anywhere else. In a single example, the way that we do that is we actually have hierarchical credentials. So if I belong to an organization and I'm allowed to act as this organization and that organization, then you have an issuer and a subject. The issuer is me issuing a credential, and the subject is the thing that I'm doing work for. But most people don't have that kind of nonsense. And then we have hash algorithms. So we're going to be hashing the request and the response, and we're going to have identifiers for that. There are no, at least I haven't found any registered IANA values for that. So we just kind of made up our own, and I made this one super easy because that's the actual function you use in hashing for Python. So when you use hashlib, you pass it that, and it gets the right stuff. So that made it super easy. On ours, we have a different scheme, but it doesn't matter, right? Pick what you want. So the request start handler gets the token from the request. And this one's a little more complicated than the one we built was. So it does the same thing. It should be getting the authorization header, not the authentication header. And then, so we're using EXJWT for here. It's our example JWT. It doesn't matter what you name it, right? Whatever you want to name it, you name it. Just don't name it bearer. You also don't want to name it basic. You also don't want to make it extended. Don't take one that's in the namespace already. So EXJWT worked for us. So we're actually just doing a regular expression to get the token out. So basically everything after EXJWT space is the token. So pretty simple little regex there.
Why not a split?
What's that?
Why not a split of the string?
It would work. It might not have worked for other things. If you have a space in your value, it doesn't necessarily work. I'm a regex guy. So split would have been fine. You're right.
Oh, just curious.
Yeah.
How it is.
Because I didn't think of it. It's a much more elegant solution. Split on the space, and the second one is the one you want. So
Because of the elegance, because of the speed.
yeah. Okay. So basically, yeah, if it finds a token, it returns it. If it doesn't have any matches, then it goes and gets the token group, which is the token group. So it would have been way simpler with split. So we go get the token. If we don't have a token, we say that we need the token, and we do a 401. Same thing we're doing now when we don't have a nonce, right? Same process, it's a little more complicated. And then we go verify compact, right? So what this basically says is that I'm going to give you the keys, I'm going to give you the token that I got out of the header, and I'm going to go verify it's valid because it has a signature. So you're giving it keys, it has a signature, and it says, great, I know the key that was used to make the signature, I'm going to verify the signature on the package, which are the claims. And if it passes, it will return the claims. Otherwise, you get the same exception you get for everything, which is another problem with JWK EST. It has one exception type. Whether it's a bad key, it's a bad signature, it's all one exception type. That's another thing I need to work on with that. So we'll raise the invalid token because it was invalid. The next thing that we do is we go validate all of the claims. Now there are JSON web token libraries out there that are strictly JWT. If you're not going to be encrypting, there are way better libraries that will actually just handle most of the default claims for you. Right? You just pass it the issuer, the audience, the leeway, and then the current time, and it will just go validate to make sure things are correct. But since JWK EST does none of these things, we're doing them manually. So basically we go and make sure that number one, we have an issuer, and we make sure that it equals valid client, which is the one that we're expecting. We go find the audience, we make sure it has an audience, and then it equals API server because that's what it should be. We go make sure it has a JSON token identifier. So the JSON token identifier is a unique ID for that token. Normally when you do the validation, if you have an auth service, you would say, here's this token, go validate it, it's going to go look up the data it's supposed to be based on the ID. Here we're just using it for uniqueness because we're using the JSON in this particular scheme, the entire JWT, that's our unique because it's got a JTI in it. We don't have to do anything to it, we can just pull the whole thing and use that as our key for our unique request validation. So we go we add the cache to the JTI. So we're making sure that you cannot send us a duplicate token. Right? It should have been stopped earlier because that would have been the duplicate request, but if you're sending the same thing with different data, that's not right either. You need to send a JTI that's unique, so we're putting it in cache. We make sure NBF is not before, so a token is only valid after, not before, or after or during, not before. So if the date is earlier than that, it's not any good. Then we see if you have it and if it matches the leeway. So basically, if not before plus the leeway is less than now. That's how you validate to make sure that the not before is valid. So a lot of if nonsense in here. And then we also go check for expired. So not before says this token is not valid before this time, and expires means it's not valid after this time. So we go find the expiration, which it should always have, to make sure that it's going to be what you want. And then we go and verify that the expiration minus the leeway is greater than that. So the expiration is in the future. Otherwise, we append a bunch of errors. And so the other thing that we're adding in here is we're adding in a request element. So JWT is extensible. They have defined values, but you can add to them. So we're adding in, on the request, we're adding in request stuff so we can include information about the request. So under request, we're putting in path, method, body hash algorithm, and body hash, if it has a body. So this one token, this one signed token that's signed using your key, will have your credential, who you are, who you're contacting, what it's about, and enough information about the request that if anybody changed it in transit, that you would be able to identify that and fail it. And you can add whatever you want in there. In our particular API, we don't use query strings because those have been logs. So we think that's a bad idea. Maybe it's perfectly fine for you. You probably need to add the query string as well, because that, if that gets modified, bad things happen, right? If someone put, you know, just a find star on something with enough records, they could do a denial of service attack on you. And you don't want that to happen. So we then go and hash. We get a hasher, basically hashlib new based on the algorithm in the claims for the request body hash algorithm. We put the data in the hash, we make a digest, and then we add it to the claims. And if we have any errors, we just throw a 401. It's an invalid authorization because it's a token coming in. I know there's a lot of confused faces because we're going through this really quick. It might make more sense when you see how we build on the end, right? Because validation is just like, check this, isn't that? Check that, isn't that? We're going to actually build a token here in the response, so it might make more sense. So when we get the response, we make sure that it's less than 300. We get now, so that now is always the same, so it doesn't change seconds. And we make sure it's an integer because it's expecting Unix timestamps, which do not have partial seconds. And so we take a JTI. So what we're doing, so what I do on my APIs is that I respond using the JTI you send me, so that you know that the response is for the request that I sent. That's another way to prevent man in the middle. Sometimes they'll take an old response that's still valid and send it to you for your request, and you don't know the difference. So what you do is when you generate this, the token identifier, when you ship it off, when you get your response back, you have the value that JTI should be in the response. So it's basically like saying, hi, this is request number 12, and you get response for request number 12, and you can verify that it's the response to the request that you sent. We set the issued at, which is the time the token was created, not before, which is it's valid now, and it expires now. So this is a single-use, auto-expiring, immediately expiring token. The issuer and the audience are just flipped on this one. So whoever sent it is whoever made the initial request is now the audience. So we're just flipping that, and we're creating. And here's the special piece that we put in. Like all of this is standard JWT. If you go to the if you love reading RFCs, which I've become a lover of RFCs for some strange reason, you can go to the IETF and the Jose working group, and you can see all the definitions of all these things for JWT. Because these are already defined. This is our extension, right? We create a response claim, and in that response, we have the status code, the body hash algorithm, and the body hash. You could also add other things that most people find important, like location, so that if it's a redirect, you know that it's a redirect. My application doesn't do any redirects, so we don't have to bother with it, because the status code, if they change it to a 301, or, yeah, people will know. Or 403, whichever one, I can never remember. And then, so we put in the body hash algorithm, the body hash. We create a JSON web signature, which is all a JSON web token is it's a JSON web signature with a defined payload schema. So JSON web signature is a piece of JSON, your header which defines your encryption or your signature algorithms, your issuer, and your key ID. Sorry, no issuer, just the key ID. And then it also has the third part is the signature, the middle is a piece of JSON that it's just signing. And we do a compact because you can actually just spit it out as JSON, but it's pretty ugly and really verbose. And in the response, we have to put it in the header because there is no auth header. And if you return things in auth header, some libraries just freak out if they have an authorization header in response, because that means that you didn't authenticate, and they start responding to that based on basic auth with a challenge. They think that you're doing an auth challenge, and the password window pops up, which is not good. And that's all of it. Now, I see a lot of like stunned faces, which I expect. Like, it's a very, very advanced topic. But does anyone have any questions about this? Yes.
It's not a question about this, but you did mention supporting to log requests.
Yes.
You can detect bad behavior in retrospect. I wonder if you could either say something about what you do and don't bother logging and the conditions under which you decide to log the detail.
So we log everything except credentials. So we actually have a standard logging format where all of our applications use the same, like we even have a committee. Like, it is so standardized, we have a committee it has to go down. Because most of the fields are the same. So when the request comes in, and we even actually do timings and things to see if things look hot there. And we use it for a lot of different stuff. We do it for timing analysis, we use it for request analysis, and we also use it for security. And so every piece of information we can gather, we put into a piece of JSON, stick into a queue, and it gets pulled down by a centralized process that goes and sticks it in Logstash. It goes and sticks it in Snowflake. So we use Snowflake is just it's a data warehousing application where you can do kind of like SQL-like queries against ridiculous amounts of data. And so that's where we do our analysis. So we're kind of like real-time alerting and stuff like that. We can do in Kibana. We can get dashboards using our elk stack. Graylog will do the same thing for you, although I believe it will cost you money depending on the number of inputs you have. And so we do it kind of two ways, right? We've got the one where we can see what's going on. So when we see aberrant behavior, we can go identify it and look at it at a scale where we can see, show me everything else around here. And we also, one of the things we do with that as well is we also have a global request ID. So the first time something comes into our system with a load balancer, it gets a UUID, and then every subsequent system that we call inside of our stack, we attach the same request ID so that we can follow it from the load balancer all the way in through the stack and see where it's gone. So we can see aberrant behavior like, it should never be here and that. So you can introduce your own security flaws, right? Just one little bug here or there, and you can create a really wicked security flaw. But you can write queries to find aberrant behavior that you can find bugs in your code just by saying like this shouldn't have happened when that was there. And if you're doing any kind of security analysis on your system, you may actually have rules that say this should never happen, and then you make alerts based on this should never happen. So if it does happen, you can find out about it through your logs.
In the code that you provided, are there any logging statements I can see?
There aren't. I mean, I just use the standard logger, and you can set the log format depending on what you need. So we just set a special log format with JSON and include all the information necessary. But that's just coming from the app, or coming from kind of that piece. We have a special JSON thing. Like I said, we have a committee. So we have a separate app. We stick it in a queue because it's gigantic. Like the largest one we have is like 3K. And it's ridiculous. And so we just stick it into a message queue because that's way too much data to process. And we've got processes that pull it off the message queue and start sticking it into all the places it needs to go. But like I said, for most applications, just putting it in a format that you can get it in, you can pull it into like via Logstash. You can pull it into Kibana and the elk stack unmodified, and then you can adjust it to make everything kind of look the same, homogenized. So there are a lot of things that you can find online about how to do logs and stuff like that. If that's something that you're really, really interested in, like definitely find your local security group, because the systems folks, that's their whole life. Right? Security systems folks, their whole life is finding logs, aggregating them, and finding unusual things that they can bust people on. And they'll have a lot of good strategies for you. Any other questions? Yeah.
So we've used
So that's going to depend. So what I do is I use asymmetric key encryption. And so the customer generates a private key. From that, they generate a public key, and they give me that public key. And then I expose my public key and all of my previous public keys through my API. So I have an endpoint where I can say, go get me the current public key for launch key. And it'll return the current public key and the ID. Or you can say, give me the public key for this ID that I got in my response for the key rotation, in case it's not the current one, in case it flips in the middle of the transaction. So, and then you can verify signatures with that, and you can encrypt data coming to the server. So that's the most secure way to do it, where nobody knows that. If you want to, you could probably build some sort of Diffie-Hellman key exchange thing into your SDK. I don't suggest it. But most places, right, you go log in. So like, again, if you have Heroku or AWS or GitHub or anywhere, right, you go log into your account using your username and password, and you generate your API key. And then they go copy that API key, and that's what they use from that point on. That's a common thing that you can do. Again, not super secure because, number one, it's going across the network. It's stored encrypted in their side. So we don't have to encrypt your public key because we can't do anything with it except send you data. So if you really want security, you want asymmetric key encryption.
That would be the only unprotected endpoint on the API. So the endpoint to get the current and past public keys so that I can send a request against the request.
Well, I can always. So here's the thing: is you can still protect it, right? You can require. If I'm not going to be able to encrypt. Well, no, I'm never going to. So you're not going to be able to verify the signatures. The only thing that's not going to happen there because you're not going to have the public key yet. But you can use your credentials and send it to there, and they can encrypt it back to you. So, and the whole thing is there is going to be a piece there where it could be problematic, where you're setting the public key. But ours, like I said, you can send the public keys to there, or you can log in and put in the public key. It's not a big deal if somebody gets your public key. But again, yeah, that is the rub there, is that getting the data where it needs to be and making sure that is data that's expected. That's the hard part, which is why they have Diffie-Hellman key exchange. So that nobody needs to know, like, if you don't know what Diffie-Hellman key exchange is, it's a way for two parties to not know the same information, have two separate values, and on their own, without ever sending it across, come up with the same value. It is voodoo magic, and you should read about it because it's amazingly awesome, and that's how the internet works. All right? Literally, how the internet works. That's how when you create a TLS session with the web server, it uses Diffie-Hellman key exchange to come up with a session key that is based on two separate numbers that the two of you have that are secret that you never share. Cryptography is amazing. Any other questions? Yeah.
Yeah, I was wondering when you're setting up APIs, how much of this code is boilerplate for you?
I don't set up a lot of APIs. And it really depends. Like, most of it's rules-based. So this is super simple. As an example, most of the stuff that we do, we have rules for replay. We have rules for rate limiting. So it's very system dependent. But again, most of the boilerplate stuff is the encryption, decryption, and the JSON web token. That stuff's very boilerplate because we use that on all of our systems. They're all the same. And we can share, like, unfortunately, like, ours is the only one Python. Everybody else is Java. But again, through all of our stuff, we just share those same libraries and the shared library to do all the JSON web token stuff because it's all the same. One last thing really quick. So you can take a survey. I think it's about this course. They gave it to me. So please, and I love feedback, right? Like, this is the second time I've given this one, and every time I've gotten valuable feedback. This is the first time I've done it for Python, so that's why we had all that crazy environment nonsense. Because I had to port it from PHP over to Python, which should have been simple. So please, 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 please do survey stuff. And again, any questions, I think you can still contact me through the stuff there. My Twitter handle is at the bottom, which you may not be able to read. It's just Adam_Englander on Twitter. Hit me up. Always around, love to talk about this nonsense. And I'll be here until Tuesday. So I'm here for sprints for one day. and then throughout the conference. So if you want to, you absolutely hit me up. You want to talk about it? I love talking about this stuff. Anything you want, anytime you want. Well, within reason. And any final questions? Awesome. It is 4:39. I cheated you out of a minute. I apologize. Thank you.